want to be recorded, you're free to leave. Your voice will be recorded. Please feel free to interrupt when you have questions, and I'll try to look at the chat as much as possible. Anyways, question one. For what value of c would make the function f of t equal to sine of 2ct over pi times cosine of 2ct over pi periodic with period 2? And so here we can see a nice thing such that sine, both of these are 2 pi, well, I don't know where to start. We know that if f of t and g of t are, what do you call it? If f of t and g of t are t periodic, how would I word this? Then this means that the product, maybe I don't want to use f and g, I'll use x and y. That x of t times y of t is also t periodic. So we'll use a nice property. And so we first realize that this is sine and cosine, and the arguments are the same. So because the arguments, is there an e in there? I don't know if there's an e in there. Uh, I'm getting a call. Hold on, decline. Um, Let me just tell them. There we go. Anyways, the arguments for both functions are 2ct over pi. And that like um this means that sine of 2ct over pi and cosine of 2ct over pi have the same period. And so what all we need to do is it just suffices to find a constant c such that that just makes each individual one t periodic, or in this case, particular to 2. So now all we need to do is say, now we want sine of 2ct and cosine of 2ct to be 2 periodic. And so what happens here is all we need to do is do the following. Well, we know that sine as a function has a period 2 pi. And so we know that 2ct, 2ct plus capital T, well, we want this to be equal, or I wouldn't say equal. Hold on. We want this to be equal to this, of course, modded by r period 2 pi. Does everyone see what I'm doing here? Is that, well, essentially what I'm doing is because I'm fixing my period to be 2, all I need to do is have this argument in here to be equal to, or maybe it's better to write it this way. I want 2ct plus 2 to be equal to 2ct over pi plus 2. So essentially what I'm doing is if I move in one period in t, like if t increases by 2, oh sorry, if t increases by 2, then all I want to do is I want to move forward by 2 pi. Does this argument make sense, everyone? I just want to really make sure. Because what is happening here is that I'm basically saying that I have a function that is f of t is equal to f of t plus t, capital T. And we also realize that each of these inner functions are 2 pi periodic. And so what we need is the following. I don't know how I want to word this. Maybe I'll have a, mu. We want to name it like this. Um, it'll be another function. I'm pretty sure it's like t plus 2. Hold on. I'm gonna see how I could word this as best as possible. Or unless everyone already understands and I don't need to elaborate more. Hold on. Question. Why don't we just say, yeah, exactly. Like, there's like a lot of simple ways to do it. I just want to make it as algebraically coherent as possible. But you could just proceed with this way. And I guess I'll move on and I guess I'll just come back to it if anyone has questions. We have like this. Oh, this is 4c. And then now we could multiply this, subtract this part from both sides. 4c over, or yeah, 4c over pi is equal to 2 pi. And thus we get that c is equal to pi squared over 2. Uh, yeah, pi squared over 2. Wait, hold on. Clearly I'm missing something here. Pi squared over 2, pi squared over 4, 2 pi, cosine 2 pi. That it? Huh. 2. I'm trying to see what I'm missing here. T plus pi. Let's see. 2c, 4c. Hold on. I'm trying to see what I'm missing here. Can someone like, you also get pi squared? Hold on. 2ct over pi with period 2. And I'm increasing t by 2, and that's good. And then, um, yeah, I'm not seeing I guess I'll just, there we go. And then 4c over pi is equal to that. And then c is equal to pi squared over 2.
Thank you.
Wait, that's weird. Is this huh. I guess this is a typo. This is very weird. Um,
Excuse me.
yes,
Can we also just use the identity of like sine of x times cosine of x is equal to 1/2 sine of x? Oh,
that
sine of
too.
2x?
Yeah, that is also possible. I'm trying to see what I am actually missing here, though. Um, because definitely this is not an approach. Um, let me actually.
If we were to include that rule where it becomes 1/2 sine, then it would multiply half to the period or to the
Yes,
AC.
that is what I'm also thinking. So I'm trying to make a nicer approach that I can construct from this. Maybe I could do a better thing. Delete. Okay. Maybe do something else that's a little easier. Um, oh, okay. So here's a different approach. Um, I take the Fourier transform of f of t and try to recover f of omega. And what I will obtain is the following. Uh, hold on. So I want to do the following, where this will be 1 over 2 pi, and there'll be the Fourier transform of this, which is some constant. I'll just write it out. Delta at omega minus 2ct over pi minus delta 2ct over pi. And I convolve this with, hold on, I think it's asking for a period of the product of sine and cosine. Yeah. Or that, actually. That is a good observation. I guess you could do that too. Um, oh yeah. One nice observation that someone made in the chat is we have the following property where if I have sine of t to cosine of t, this is equal to sine of 2t. Oh yeah. And then this means that f of t is equal to just 1/2 sine of, what is it? 1/2 sine of 4ct over pi. And then we're done. Oh yeah. Let me just make sure I'm not doing anything wrong. Yeah, huh. And so what happens here is now all we need to do is force, now we just need to do the matching thing where we do 4ct plus 2 over pi is equal to 4ct over pi plus 2 pi. And so what happens here is now we could just do our, we could just distribute. And then recover the fact that c is equal to pi squared over 4. Thank you in the chat. I haven't seen this question in a while. But yeah, nice observation. I guess this is a knowing your trigonometric properties would really help in this question. Um, questions.
Oh, why do you add by t plus 2 in the parentheses? Is it just because you want the period to be at that point?
Yes. And so the way this, like the way I like to think about it is if I have some sign, if I have specifically sine of some function, then, and I need this to be equal to this, right? Then all I need to do is match the arguments to each other. Like if I move forward by a certain number t, capital T, then this kind of translation in the inside argument must be equal to kind of pulling out a 2 pi because we know that sine itself is 2 pi periodic. Is that clear or that's how I obtain and do this kind of step.
Got it. Yeah.
And this is just in general for anything where even for cosine that it works the exact same. But otherwise, if you have an outside function that is like a certain period that has a certain period, then all you need to do is match up the translation of the inner function and make sure it kind of like you could pull out the capital T and make it into like plus whatever the period of the outside function is. Yeah, that took way too long because I didn't see the nice identity, but you know, it's nice to know trigonometric identities. The steady state circuit below has input voltage V in cosine of t and output current I out of t. If C is 0.5 farads and L equals 1 Henry and R equals 1 ohm, 2 ohms, then what is the magnitude of the circuit's frequency response? Okay. Um, for this one, I feel like it suffices to show, I mean, we know that this has a Thevenin equivalent, or you could kind of simplify it down into the following, where it's just one component, ZEQ, and then we're just analyzing our current I out. And so all we need to do is it just suffices to show or find ZEQ. Why is that? It is because let's see. Because we know that if let's say we converted V in to our input, x of omega. So let's say this is converted to our phasor form, phasor 1, e to the j0. And then I out has our phasor form of something. Let's just call it like y. Then we know that y is equal to just 1 exactly times ZEQ evaluated at a certain omega. Or more so like our h of omega, which is certainly most related to our Thevenin equivalent impedance. And so all we need to do is just find our Thevenin equivalent impedance, which is really nice. And so let's do so. ZEQ is equal to R plus L parallel C, which is equal to, I'll just keep everything symbolic for now. This is L j omega L 1 over j omega C divided by the sum. And now let's find what omega is. Omega is equal to 1, and L is equal to 1, and C is equal to 1.5. And so what we obtain is, actually, maybe I want to evaluate them all separately. This is just J exactly. 1 over j omega c is equal to 1 over 0.5j precisely. And then this is equal to negative 2j. And so this solving this becomes actually very easy. You just get 2 plus, take the product of those two, which is 2, over negative j, which is equal to 2 plus 2 plus 2j. And so now we could say that in particular, the magnitude of our frequency response is just equal to the magnitude of our equilibrium, our Thevenin equivalent impedance when omega equals to 1, which is just equal to the magnitude of 2 plus 2j to 2 squared 2. Or, okay, what is going on today? I am not doing something correctly. Hold on, let me try to debug this. Omega equals 1, cosine of t. Oh, and then, oh my goodness. And I am not doing this correctly because the I out, if I say I out is, okay, sorry. We have V equals IZ. And this means that I is equal to V over ZEQ. And so actually our input impedance, or like our, if we want to convert this into the form where we have it in the frequency response form, input voltage, then we have that our H of omega is actually 1 over the impedance. Yeah, that is a big fumble by me. I'm rushing. I'll try to calm down. I think I'm rushing too hard. So this will be 1 over the 2 plus 2j. And then this is 1 over that. And thus we obtain square root 2 over 4. Whew. And thus we get the right answer. Sorry, I'll try to take it way slower because I think I'm going too fast and making too many mistakes. So yeah, otherwise, please don't make mistakes like me. I guess it's very important to kind of really write out the input-output relationship as a nice equation. And so you get that your input-output relationship is this ratio, which we need to consider as our kind of frequency response form or the LTI system form. And then we could deduce our final answer from as follows. So this tells us, maybe I want to write it out. This tells us that h of omega is equal to 1 over ZEQ at omega. Perfect. Anyways, I'm going to keep moving. If u of t minus 2 plus 1 is the input signal to an LTI system with impulse response e to the negative t times ut, then what is the value of the output signal when t equals 3? Okay. I think that this would be a nice just time domain convolution problem. Yeah. Or I mean, you can do multiple things. I'll just do a time domain convolution method. And so, or never mind, I'll do the Fourier transform way. Or I don't know, it's really weird. I guess I'll do time domain way, and maybe I'll do the Fourier transform way if time permits. And so my gut reaction is to just examine the convolution between these two functions. And so I'll take an integral from this e to the tau u tau, and then I will take t minus tau minus 2 plus 1 dt. Sorry, d tau. And so from here, You can break it up into two different integrals. Um, t u tau u t minus tau uh, t minus tau minus 2 and then plus u tau d tau. Perfect. Question. Any point in taking a Laplace transform fits nicely into those formulas? You can actually. I don't think it's a bad idea. I'm just doing time domain because like there's always many different ways you could solve these kinds of problems. I'm just choosing a way that that comes more intuitive to me. But you know, if another method can come intuitively to you, and it can work for everyone. And so yes, you could do a Fourier transform or a Laplace transform method. Nothing's stopping you. It's just I'm just choosing this way because time convolution time is also very helpful practice. Um, Anyways, so here we have to analyze unit step functions. Analyzing unit step functions is going to be very important. And how it interacts with integrals. And so what is this? Well, let's actually, starting from this point, let's make sure to set t equals 3. Then, and simplify our expression. E to the negative t, I could kill off that, so I could say this 0. U of 1 minus tau d tau plus 0 to infinity e to the negative tau d tau. And so very, very nicely, this is already equal to 1. We already know that. And then the second one is actually also very easy. It is 0 to infinity, or it's not really infinity, it's just from 0 to 1, because this unit step function looks like this. This is 1 if tau less than 1, and then 0 else. Or, yeah. And so what this means is that we could kill the integral bounds again, and then we can obtain something like this. And then what this tells us is the following. This tells me that my first one is negative e to the negative t, 0 to 1, plus, and then this integral is just 1. This first integral is 1 minus 1 over e plus 1, and so we get 2 minus 1 over e. And then that's the answer. So you can't take the Laplace transform, and actually, it might be helpful, so I'll actually just do it. I think I have time on my hands. And so u of t plus 2, so let's try the Laplace transform way. The Fourier transform way will follow similarly. U of t plus 2 plus 1, sorry, t minus 2 plus 1. I recall that the Fourier transform of this will be, or Fourier transform of this will be 1 over s plus delta of s. Then the translated version should give me, please correct me if I'm wrong, but it should give me e to the st, negative st, 1 over s delta plus delta s. Or is it positive st? I recall it's negative st. We'll see at the end. And then, and afterwards, I could just analyze 1. So it's, actually, that's it. Oh, and then there's a impulse response. So e to the negative st u of t has a has a Laplace transform of 1 over, wait, negative t, sorry. Oh, and t equals 2. There we go. This is e to the negative t. This will have a 1 plus S plus A for transform of S plus 1. Perfect. I believe everything looks consistent here. And all we need to do is take the product of these two. This is my x of s. This is my h of s. And so we know that my output is equal to the product of the Laplace transforms, which is just e to the negative 2s, 1 over s, 1 over 8s plus 1, plus delta s, 1 over s plus 1. Oh, and I guess like at this point, evaluating this is not super duper easy, I guess. And so because you have this kind of thing where I mean, yeah, sure, that's a translation, so you can kind of ignore it, but considering the Laplace transform of this will take you more steps. This will give you partial fraction decomposition, and this is actually this one's pretty easy. This is like you could evaluate this, but again, this is more steps. And so I guess that's the just the time convolution way is slightly shorter. So there's kind of like your feel on kind of how to save time. I thought I chose to do time convolution specifically because I saw unit step functions. And unit step functions are very nice in integrals because it just kills off a lot of the bounds. You can see that I kill off bounds very, very quickly because I have unit step functions that are like going in opposite directions. Is Laplace transform of 1 just delta S? Yes, I believe so. Yes. Um, maybe off by a factor, but I know that delta T has a Laplace of 1. Laplace transform of 1. I'm pretty sure it's just delta. Um, let's see. Because it's kind of like very ill-defined, mainly because, or it's not. Or is it? Huh, wait. The function of 1 is, I swear, there should be like a duality here. Um, T. It's weird. Maybe I will actually check on this. If we brute force one, yeah, you should get something else. Or maybe it's just 1 over s. Also, I don't think the main issue with that is that you won't get something that is like convergent. Like you take a look at this. You try to evaluate it, and you get negative 1 over s, and then you get negative e to the st, negative infinity to infinity. And I don't think this is very well defined. So perhaps not. I kind of immediately went across the Fourier transform extension, but probably not. Can you go back to the time to section? So yeah, maybe this isn't the greatest maybe this isn't the greatest approach that I have considered. So I'll just kind of get rid of it. Uh, but otherwise here's the time domain solution. So essentially what I did was I kind of killed up a bunch of the bounds by using the fact that u of tau is 1 for tau greater than 0 and 0 for tau less than 0. And so that's how I did this first integral evaluation where I kind of got rid of that to kill the bounds. And then I kill the bounds again by evaluating the unit step function. And I realized that the integral is 0 at a lot of points where I'm evaluating it. Can you explain the term of the bounds? Can you go back to time? Okay. Yeah, that was that. Again, I'd be happy to like elaborate on any particular question and come back to it. But if there's no questions, I'm gonna keep moving. Whew. Oh wow, there's a lot of people here today. Hold on. So, problem 4. Consider the two systems whose input-output relationships are shown below. Which of these statements is true? So, okay. We have first x of t. So let's think about system A. Let's do the classic thing where I let x1 of t yield y1 of t and x2 of t yield y2 of t. And remember, when I write out things, you don't need to like write them out at the same time when you're actually taking the final. Most of them should come from like what you already know. And so let's take a look at the first function. If I put in alpha 1x, sorry, alpha x1 plus beta x2, then what my output is the derivative of that, of whatever I put in. I mean, I'm just gonna omit the t's. I'll just print the t's. And then what I realize is that the derivative operator is actually linear. So what that means is that I could push in derivative operators across constants and distribute it across different numbers. And what this is literally just the linear combination of my outputs. So we check that A is linear. Secondly, let's consider the time invariance of it. So maybe I'll just use the space on the top. So let's check for Ti. Let's say I put in X that is time delayed into the system. This is derivative of the time delayed signal. And maybe that, yeah. And this is the derivative of the time delayed signal. And perhaps I will do this. I don't know. It's kind of like this comes from convincing yourself that this is time invariant, kind of comes from how you built up your derivative intuition. And so if I give you a specific function and I say, okay, the derivative, this function will tell you the derivative at this point at time equals t. Then, um, let's say I give you a shifted time function. So this is, let's say, or maybe I shift it forward so that it's easier. This is shifted forward by T naught. And I ask you to evaluate this at T plus T naught. And so what happens here is the fact that if I give you a delayed signal, then it will take the derivative of the delayed signal. And the derivative of this precisely delayed signal, I'm sorry, I'm just running out of room. Maybe I'll just move it to the bottom. Or maybe I'll move everything to the bottom just because I have more room. TI. There we go. So I'm going to give you a time delayed signal, and if I take the derivative of it, then hold on. I know I got a comment. I see. Yeah. Okay. Um, I'm going to address the comment in the chat afterwards. But essentially, what I'm saying is, if I take the derivative of a delayed signal, then what I'll get is that the derivative of the derivative of the delayed signal will just be here. I will actually just draw it out. I feel like it's just better. Maybe an example would be nicer. I'll give you a cubic function, x cubed, and I'll give you a delayed cubic function. Maybe like over here. This is x minus t naught cubed. Then observe that no matter what line I give you, the derivative will just be a shifted version of the derivative of the original function. Like do you see that? Do you see what I'm doing here? Algebraically, I'm sure it mostly just works out. And by that, it's probably just doing like a change of variable where um, maybe like I'm taking, it's going to be really weird notation, but this would be equivalent to taking the derivative of like t minus this. Or, maybe it's better to just leave it at this. Yeah, maybe it's just better to leave it at this. But we could just define like this particular example where you could convince yourself that the derivative of the delayed signal is, or a moved of shifted signal is just the derivative shifted. So derivative of shifted signal is just equal to your shifted derivative. And maybe I'm pretty sure I could just show it using the using just a definition of the derivative at page. Okay, maybe I could just show it. So currently we have, and maybe it's better for notation to just do this. I'll say d tau, and then you evaluate this at tau equals t. Then what is this? Or more so, maybe I want to show that if I assume time invariance, then algebraically my derivative is as follows. This would just be tau at t minus t naught. And now I want to consider this following function, right? Essentially what I'm saying is this is my time invariance assumption. If I assume time invariance, then I expect that all I do is I just evaluate the derivative at a shifted position. However, or if I truly put in, or my true output, this is my true output. Then I'm inputting this. This is my input. This is my input. And then my output is this evaluated at tau equals t. And all I want to do is I want to show you that these two are equal. And I guess I could use just the property where I just do, hold on. Let's see here. I do just minus this. As, or, as h goes to 0 for, or yeah, tau equals t. So h. And then what I wrote out here, if we kind of just take a like very short analysis of it, then we realize that this is actually just the derivative of x of t, but just evaluated it, sorry, x of tau, evaluated at tau equals to t minus t naught. Like that, just because I'm just getting it from this. Sorry, I'm just trying to make it very algebraically sound. I hope I'm not just confusing everyone more just by trying to like write it out completely. Essentially, what I'm saying is that if I take the derivative of a shifted function, then essentially I'm just shifting the derivative. That's what I'm just trying to say in this entire part. And thus, we algebraically showed that it's time invariant. And maybe also, this is probably the more convincing example, but we could just show it graphically completely. Any questions? I'd be happy to clarify anything that I just said in the past like 10 minutes, because I'm sure it's very convoluted. But essentially we have linearity just because the derivative operator is linear, and then we have time invariance because if you shift the input and take the derivative, it's the same as taking the derivative and then evaluating that derivative at that shifted point. We have this kind of nice parallel. So we get that the derivative operation is LTI. So this is LTI. And now let's check out this part. And hopefully this one doesn't take too long. We have inputting alpha x1 of t plus beta x2 of t into our system, and we obtain t times exactly what we put in. And then let's kind of like break this apart. This is alpha times t times x1t plus beta times t times x2t. And then we realize that the input for x1t, which is y1t, is precisely just equal to t x1t. And similarly, this yields the following. And so what we obtained is that this is just equal to alpha times y1t plus beta times y2t. So I inputted a linear combination of the two of inputs, and then what I obtained was just a linear combination of inputs. And so we get that system 2 is linear. Now, let's consider time invariance. Well, let's say I give you xt minus t naught. Time invariance tells you that, well, what I will actually get is this, but your time invariance expectation, is to obtain this. And clearly, these two are not the same. Oh my God. Clearly, these two are not the same. And so we get that system 2 is not time invariant. Let me close that. Any questions on how I showed that it's not time invariant? So I feel like I said this on the previous exams as well, but showing time invariance is actually kind of like a very systematic process, except the derivative one, which is a little more contrived. But for time invariance, you do two things. You input a time delayed signal and you check what actually comes out. This is your real output. And then what you do is you assume time invariance, and then you see what you're expecting, and you just compare the two outputs, your expected output and your actual output. If these two don't match algebraically in any way, then you know that is not a time invariant. And so this is L but not Ti. And then since we get A. Just to pop back to the previous question, this one. Apparently it was mentioned in lecture that taking the Laplace transform of this doesn't exist. I just directly quoted from lecture. So yeah, it's kind of hard to approach this in a Laplace fashion. Maybe in a Fourier fashion. No, not even in the Fourier fashion. Because you cannot take it in the Fourier domain because the Fourier transform of this does not exist. Or, I mean, it does exist, but it won't be very fun to deal with, no. I guess you'll have like just like a j omega plus delta omega, but I'd say that the time domain convolution will be significantly easier to do. Otherwise, I'm gonna keep moving. I'm like we're 45 minutes in and we've done 4 questions, so I gotta keep going. What is the inverse Fourier transform of the real valued function f omega shown below? So for this, you may look at it and be like, okay, well, how do I do this? It's like, do I approach it in unit step functions? And when I look at these answer choices, every single answer choice has a sink in it. So because we know like every answer choice has a sink in it and has sometimes has a complex exponential, my gut reaction is to just say, oh, it's just a it's just a modulated sink function that results in a translated rect. So does my what do you call it? Well, this is kind of like my ground plan, like my floor plan of how I'm going to approach this problem. And I took clues from the answer choices and the graph in order to make this decision. And so all I need to do is kind of backtrack my way from the translated rect function to my desired inverse Fourier transform. And you don't need to take a single integral here. All you need to do is kind of do some like keep track of pairs. And so clearly, this is a rect function that is translated, that is of width. What is this? So height 2, it is of width 5, and it is, what is it? Centered at 2, at 5. Yeah, at centered at 5. And so what this means is that we could formulate f of omega to be 2 times rect of omega minus 5 divided by 2 omega naught, where omega naught is equal to 5 over 2. Questions so far? Okay. All right. So with this little start, now we could just start backtracking. Well, we know for a fact that this will have a inverse Fourier transform. Let me rewrite it. This will have an inverse Fourier transform of some function. Let's call this, let's call it just g of t of e to the neg 5jt. E to the 5jt. And I derived this from the fact that, like, because I have the Fourier transform pair where if I have ft e to the j omega t, then the Fourier transform of that is f of omega minus omega naught. And so basically, I kind of made a pair between this part and this part. Okay, perfect. And now let's consider the Fourier transform of g of t. Well, now g of t, the Fourier transform will be 2 rect of just omega over 2 omega. And this must mean that g of t is very easily you could evaluate g of t very easily. This would mean I don't have this off the top of my head of the rect function, so I will do it. Maybe I want to cook this up in the format that I like. And so I will say, I'll divide by pi on both sides or more so, I know that the Fourier transform pair of sinc of omega t is equal to pi over omega t times rect of 2 omega naught. So I have this Fourier transform pair. And then all I want to do is I want to prep it up to a nice way. I could shift over my constants to the other side. There we go. Perfect. So basically what I did was I used this Fourier transform pair and I shuffled some constants around in order to put it into this form. And now this form looks very similar to what we have right here. And so I could deduce g of t to be precisely 2 omega naught over pi times sinc of omega naught t. And so now I know that the inverse Fourier transform of f of omega is this. These are equal. And so what this means is our final answer is just g of t given as follows. Remember, omega naught is 5/2. So I get 5/pi sinc of 5/2t and then e to the 5jt. And thus I could get my final answer. So basically what I did was I just kind of, how did I get the omega naught value? I got it from the width. I got it from the width. Omega naught will always be just the width divided by 2. So basically in this, like my floor plan was basically, I realized that my Fourier transform was a shifted rect. This means that in time I'll be modulating, and so I just did some like Fourier transform pair chasing in order to get my final answer. How do you get the value for omega naught? Yeah, so I got the value for omega naught by using the width. And people might be asking like, oh, why did I put my rect function denominator in this form? I did it precisely because it's kind of easier to like convert between rect and sinc if I like chop it up like that. Otherwise, um, that's how I get my final answer. So problem 6, it's almost an hour already. Uh, if LTI system has frequency response, that, and input of those, then what is the output of the system? Okay. For this, we realize that each of these input values, so remember, it's an LTI system. Question. The rect is still shifted and scaled. Yes, the rect is shifted and scaled. I mostly consider the shift because that is what gives like the modulation part of the time. So remember, first of all, we realize that if I put this, let me actually e to the 0jt plus 2 e to the 4jt plus 2 negative 4jt. This is into our system. Then from what we know that this is going to give us, let's say this is h of omega. By the eigenfunction property, we know that this will give us h of this 3h of omega e to the 0jt plus, oh, sorry, e 2 times 0 h of 4 e to the 4jt plus 2 times h of negative 4 e to the negative 4jt. So this is just the eigenfunction property plus LTI systems. And thus, now all we need to do is evaluate that, which is actually not too bad. This is equal to 3 times uh, 3 times 2 plus 2 times h of 4 is 8 plus 8j over 4 minus 4j e to the 4jt plus 8 minus 8j over 4 plus 4j negative 4jt. This is we factor out 8 and 4, and we obtain 4 times 1 plus j over 1 minus j. And then what do we want here? We have 4 again, 1 minus j, 1 plus j. E to the negative 4jt. All right. So with this, And the question is, where do we go from here? Well, you have to evaluate these complex numbers. And here's a pro tip, but I like to think of if I see division of complex numbers in this kind of form, then I automatically think about the polar form instead of just doing rectangular form. This is square root of 2 e to the j pi over 4. And this is square root of 2 e to the j negative pi over 4j is equal to the 1, j. And furthermore, 1 minus j over 1 plus, this would just be 1 over the inverse of what we had right above, which is just equal to negative j. Okay? And so what we obtain is this is 6 plus 4 times j e to the 4jt minus j negative, negative 4jt. So we have this so far. And now from here, hopefully I didn't make any particular mistakes. Good, good. Okay. From here, I want to convert this into sine. And it feels like I have did I make anything wrong? So I want to be really sure that I didn't make any mistakes here. 4 plus 4j, good, good. Yeah, I think I'm in the clear for now. That's 4. And then we want to put this in a form that we can digest very easily. This is 1 over j, or maybe I want to, yeah, I'll just leave it at that. This is negative 1 over j e to the 4jt plus 1 over j e to the negative 4jt. We factor out the minus, and I'm definitely doing, oh my God, what is it? What is it with me today? Or I think I'm fine actually. Minus 1 over j e to the negative 4jt. And then this is equal to, this is sine 2 sine of 4t equal to 6 minus 8 sine of 4t. There we go. And then we get the answer. Factor out 4j made it easier for you. Yeah, you can do that too. I just like to keep this in a form that I just like to digest, which is subjective to everyone. But yeah, still, the algebra is very straightforward. I guess you should get comfortable kind of thinking about complex exponentials as well. Otherwise, it's been an hour. We're on problem 7. You gotta pick it up. What is the value of the Fourier transform at x of omega? At omega equals 0. Very important. So for this, it's kind of important to see that that whenever you're asked for a Fourier transform at a value at 0, it's very evident that all you're doing is taking the integral of the function itself. Oh, we take omega to be 0, and then we realize that this just goes to 1, and thus this is just the integral of x of t dt. Okay? And now let's take a look at what our function looks like. Well, I don't know if everyone has exposure to this function, but it's called a Gaussian. And if t is greater than 0, it's a Gaussian. It's going to look like something, some curve. Well, regardless of what it looks like, whatever's important is to look at the other side, where we see that on the other side, it's the negative of it. And the question is, do you need to know what this curve looks like? No, not really. So just from looking at this curve, we realize that the integral over the entire thing is just 0. But what you can also do is you could see, oh, well, it's kind of like a piecewise function. It's kind of defined as a different number on both sides. And so you could cut it up into two different parts because the function is cut up into two different parts. Plus. And then all you do is you make this little substitution where for this particular one, you say, oh, I'm going to let be t prime equal to negative t. Then dt prime is equal to negative dt. And so you do u sub on the left function to realize that this is e to the negative, this is the same as t prime. Yeah, I'll just keep t prime. And this is negative dt. Bounds stay the same. And remember, the bounds have to be changed because remember that if negative t is equal to 0, then this implies that t prime is equal to 0 as well. And if negative t is equal to negative infinity, then t prime is equal to infinity. So we have to change these bounds. And so this bound must be, actually, I'll keep it like this at first. Boom. Here, I'll cook it up into a form that we like. So this is the form that we have. And all we do is we replace everything with respect to t prime now. So the everything at top will be t prime. This is now dt prime. And then our bounds change from infinity to 0. Plus infinity t. And now we realize that for this particular integral, we could flip the bounds by taking a negative and then flipping the bounds. And then we realize that this first integral is basically equal to the second integral, but you just change the name. You're just taking the integral with respect to t prime. But the bounds are the same and you're subtracting it. And so wouldn't it make sense that these two integrals will just cancel out? So it is observed that e to the negative t prime squared integrated with respect to t from 0 to infinity is exactly equal to the integral with just a different name. And so thus we obtain that this integral is just equal to 0. And thus it is 0. Another observation you can make is that this function is odd. What that means is x of negative t is equal to negative x of t. Wait, yeah. And so this directly implies that we already have x of t equal to 0. There's a lot of ways you can do it, but it really depends on like, do you like which way you just prefer or which way comes to you the most naturally, which is the most important. Anyways, let's keep going. Try to pick up the pace. What is the magnitude of the coefficient f of 0 of the exponential form of the Fourier series for the function f of t is equal to sine t to the power of 4? Okay. So let's take a look. Um, hmm. Oh, we realize that f of 0, as we know, is a 0th Fourier coefficient. And all we do is we just need to do the integral over the period. Well, I guess we have to consider the period of this. The period of f of t is well, recall that sine squared of t has the following graph, which has period pi. And so it takes a bit of convincing, but try to convince yourself that sine of 4t will also have a period of 5. Sorry, the period of pi. Like it will still look like the same humps of length pi. So because it's just sine squared of t squared. So try to convince yourself that the period of f of t is pi. That's the first step. And now all you need to do is you could try to just take an integral. Or you could do a lot of things, but let me first write it out. And maybe this actually won't look too fun to do. I will not do this. In fact, I will do a different way by doing the following. We know that sine of t is equal to pi, no, 1 over 2j e to the jt minus 1 over 2j e to the negative jt. Then, what is sine squared of t? This is equal to, well, this is just polynomial expansion. We just need to multiply polynomials. And so, because I am lazy, I will call 1 over 2j as c. Because I don't want to write fractions constantly. Then what we know is that we just multiply this like a polynomial. Then we get c squared e 2jt, because it's like e to the jt, e to the jt. And then we have 2c squared e, actually it's just 2c squared because the, maybe I want to write it out. 2 minus 2c e to the jt, negative jt plus c squared e to the negative jt, e to the negative jt. So you have this kind of formulation. And then we could just expand this or combine a bunch of terms to get the following. C squared e to the, hold on, e to the
Wouldn't
negative
it be minus
2gt.
4c?
Uh, hold on. Pardon? Can you say that one more time? Whoever.
So when you did 1 over like c e to the jt times negative c e to the negative jt would be um minus 2c squared, right?
Oh yeah, 2c squared, sorry.
And then you did that again with negative 1 over, I mean, negative c e to the negative jt times c e to the jt will give you another negative 2c squared, no?
Negative 2c squared. Uh, Pardon? Like, wait, which part am I missing out over here?
I believe that you're missing out an extra negative 2c squared.
Negative 2c squared.
Oh wait, no, you just get no. Sorry. That was that was my fault. That was my
Okay. So
fault.
I'm good here.
Okay,
I'm good
you're
here.
good. You're good. Sorry.
Okay, perfect. And so now we have this kind of polynomial expansion, and all we need to do is do it again. Um, and you can save some time by not writing it all out and giving your own nice notation. But actually, we are only interested in the Fourier series coefficient of f of 0. And what is that? That just means that this is correlated to the one that is e to the 0 jt, essentially the constant. And so we realize that this is equal to, this is like a time-saving technique. Of course, this is a polynomial, a product of two polynomials, which is not very fun. But what if I tell you that you don't need to you don't need to expand this entire thing? All we need to do is kind of pick and choose the combinations that will yield us the constant term. And so what we do is we choose these two. Let me do this. We choose this and this. And then we choose this and this. And so And I don't think any other combination should yield us an answer. Yeah, so we realize that only three combinations from each from the two polynomials will yield us the constant term f of 0. And like let me tell you like why I'm doing this. Well, let's say I multiply this and this together, then it will give me c to the power of 4 e to the 4jt, and that is clearly not my f0 term. And that follows with every other combination except these three. And so like all we need to do is kind of consider these three ones. Uh, and so maybe I want to, here, I'll do these lines a little more intuitively. There we go. That looks better. And so what happens, and actually maybe I want to color code it so that it doesn't look too confusing. I'll do blue. And I'll write out that these products yield f0. Like the degree of the complex exponential will allow you to get f0. And so we realize that this will give us c to the power of 4. This is 4c to the power of 4. Sorry, 4c to the power of 4. And then the last one just gives us c to the power of 4. So what is this? Well, we really remember that c is equal to this. And also we're actually taking the magnitude. And so we sum all of these together to obtain 6c to the power of 4, which is just taking the magnitude. This is 6 times 2j power 4. And then we realize that the product of magnitude, like a magnitude of a product, is just the product of magnitudes. And so this is 6 times the magnitude of 1 over 2j power 4. This is equal to 3 over 8. And so I believe that is our desired answer. Questions? Am I using u sub on this question? For this?
No, I was referring to the last question. I think
Oh,
it
the
was.
previous one. For the
Yeah, the
previous,
previous
yes,
one.
essentially I did a u substitution. Maybe, yeah, maybe you actually, I'll change all these variables to u.
Yeah, no, it just looked like kind of weird, especially since like you had the t squared at the top, and then they'll become 2t. You don't have any other t.
Yeah, let me
Okay.
change all these because I definitely understand why it would confuse, or like it would look confusing. So let me just do this, and there we go. I think that looks a little more coherent. Yeah. Okay, but otherwise the idea stays the same. We're using u sub to evaluate the integral. Anyways, hopefully this question was interesting where you could save a lot of time just by like examining, by like correlating what you want from like the process of at which you're obtaining your answer. So you don't have to actually expand all this. Number 9, okay, like I pick up the pace. The block diagram below consists of a multiplier and a linear time invariant system with impulse response, h of t, and you're given these Fourier transforms. Which of the following choices of omega would make the Fourier transform of y of t non-zero? Okay, so clearly we see that this is kind of like a sampling problem where we have our s of t right here, and then we have our x of t, and then we have our, what do you call it? We have our low pass filter right there. And so the question is, we basically, all we want to do is make it so that our h of omega won't cut out our like input into here. So let's call this part z of t. Okay. Then let's try to think about what this would look like. We know that s of omega, well, we know that z of omega is equal to 1 over 2 pi s omega convolved with x omega. And so And remember that S omega is equal to, well, this is t equals to 1. This implies that omega naught is equal to 2 pi. And so this is 2 pi delta function spaced out by 2 pi. Everyone follow with me so far? This is what I have. And so since I'm convolving my x omega with an impulse train, we just need to kind of consider what the spectrum would look like. And so this is a parabola defined from -1 to 1. And so let's kind of see what our convolution would look like. It would be at the points 1 spaced out by 2 pi. That's too many points. And then I'm going to draw out my parabola. Remember that these are spaced out by 2 pi, so 2 pi, 4 pi. 2 pi. Two pi, -4 pi. And right now, I'm not too concerned about the height of my parabolas. I'm just going to worry about their position. Okay. So, and then what we do is we say, okay, I'm going to do a low pass filter that does the following. It cuts off everything. So recall that my output y of omega is equal to z omega times h omega. And where my h omega is the purple function. Maybe I'll make it blue because I like blue. Then what happens is that this product will yield us a very particular set of parabolas that are kind of sitting at, 0 and one at 2 pi, -2 pi. Everything else is cut out because of our low pass filter. And so what happens is now we want to choose an omega such that it kind of falls into one of these points where it's like within, like it's between 2 pi minus 1/2, 2 pi, -2 pi plus 1/2, 2 pi plus 1/2, -2 pi minus, sorry, 2 pi minus 1/2. You get the idea, right? Like essentially, I want to choose omegas such that it falls into where this graph is non-zero. So now we're thinking about, okay, which ones works? And we understand that anything too big is not good. We understand that, and some of these will not work. So let's see. I guess it's just process of elimination, where you have to realize that the only answer choice is 6.1, which is right around here. This is omega equals 6.1. Everything else will fall out of range, which is why we need to just do process of elimination. These are the ones that are clearly too far. This one is clearly like, this one is approximately maybe like -5.7. It's really up to you. Like it's really up to you to kind of estimate 2 pi and kind of see which numbers fall into the range. Plus or minus 1/2. It's sorry, it should be 1, not 1/2. Sorry about that. There we go. There we go. Sorry about that. But it's essentially up to you to kind of figure out which ones fall into the range of all of these red areas. And we realize that the only one that falls into this range is negative 6.1. So choose omega such that falls into red. Anyways, there's that question. Number 10. What is the output of a linear time invariant system whose frequency response is that when the input is this? Okay. This question, I'm going to take the Fourier transform of whatever this is. And we could just first try to expand this complex function polynomial. And then we realize that this is actually it's very easy to find the Fourier transform of all of these. And so we realize that this is just this is a delta at just located at 5, I believe. This is a delta located at 2. This is a delta located at 3. And this is a delta located at 0. This is, let's say this is f of t. Then this is f of omega. And so then we just consider our output, which is f of omega times h of omega. And this would kill off. Let me actually just rewrite it out. We have this, and then we multiply by by whatever h omega is. And let's think about it. Actually, let's just distribute. Delta at 5 plus h of omega, delta at 2 plus h of omega, and delta at 3 plus h omega, delta at 0. And remember what's like delta function properties when you multiply them against functions. All you do is you keep the delta function, but you evaluate it at the point where the delta function is located. This is equal to h of 5 delta at 5 plus h of 2 delta at 2. This is h of 3 delta at 3 plus h of 0 delta at 0. And realize that if omega is less than 2.5 or if within 2.5, then we just goes to 0. Eigenfunction. I can use eigenfunction property. It's essentially the same. Like the eigenfunction property comes from like what I'm doing right here. So yeah, I guess. Oh yeah. Huh. I don't know why I didn't see the eigenfunction property. Well, regardless, I guess I did the Fourier transform. So, you know. Yeah, both ways work the same. I don't know why I didn't see the eigenfunction property this time, but the process is the same, where we're getting the same thing back, but we just multiply by h of 5. And so now we obtain, I guess it's better just to the eigenfunction property. Um, eh, yeah, I'll just keep going. I don't think it really matters. And so what we see is that this is the inverse transform of this is just h of 5 this plus. And so you can see that I basically did the eigenfunction property, but the long way, as people would say. Yeah. Doesn't one transform to 2 pi delta 0? Yeah, that's a good point. It's 2 times 2 pi. Thank you for the catch. I believe that is right. There we go. There we go. But you know, the most of the concepts stay the same, where now if you take the inverse transform of that, you just get the eigenfunction property back. And so now you can see how powerful the eigenfunction property is. I basically saved 4 lines of work, and now I just need to evaluate this. Well, if omega falls into within 2.5, then we just kill it off. So this goes to 0, and this goes to 0. And thus what we have left is 2e to the 5jt. I think that's, yeah. 2e to the 5jt plus 2e to the 3jt. And thus our answer. Questions? No? Okay. Problem 11. If f of t is equal to sinc t times cosine of 10t, then what is the smallest b such that f of omega equals 0 whenever omega is greater than b? Wait, what? Wait. Oh, I see. So basically you're finding a b such that it's band limit. Like you're basically finding like the band limit. So let's see that. Let's see what we're supposed to do here. Well, we're multiplying by cosine, so that should be a clear hint that um, it's a modulation. And so f of omega, we know from the convolution property. So a product in time is a convolution in frequency. And so we should see here the Fourier transform of sinc, which is, I will keep ambiguous, some constant times a rect function of omega over 100. Yep. Convolved with a sum of deltas. Uh, yeah. There we go. And at first glance, like, okay, so now it's kind of important from this point to realize why I'm omitting the constant. It's because this question does not really care about like how tall a rectangle is. It's mostly worried about like where in frequency, like how wide is the rectangle. And so it suffices to kind of it's okay to ignore the constants sometimes because the math doesn't ask for it. And so let's see here. This is a rectangle of length 100. Yeah, length 100. And this is translating it. And so what I'm doing is I pinpoint my negative 10 and 10, and then I just place a rectangle of width 100 centered at those points. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So let me draw one rectangle. No, that's too large. There we go. Draw another rectangle, turquoise. There we go. And then you would take the sum of those two rectangles. This is my rectangle centered at negative 10, and this is my rect centered at positive 10. And from this, we realize that the sum of these will look like something like a little sandcastle, but it'll just be band limited by 60 and negative 60. And so the smallest such b, such that anything outside is 0, would just be 60. So you're concerned about like the pi constant on the like this constant right here. You try to ignore it because you can marginally save time just by ignoring and not worrying about writing it out. So It's like imperative to realize that we are only concerned with the length of the rectangle. So, and then we're seeing like, oh, I've shifted this way, I shifted this way, and now how can I contain this? And we realize that it's all contained right here. Of course, if you see any shortcuts, then please take it. But remember, I'm always writing out all my work so that like it's very coherent for everyone to see. Um, but if my gut reaction is, oh, I have a rectangle that ranges from -50 to 50. I shift it to the left, it should be from -60 to 40. If I shift it to the right, then it'll be from -40 to 60. And boom, I've contained everything between -60 and 60. I'm done. Like that is like when I looked at this question, I was like, oh, I would do it that way. But of course, drawing it out will always be helpful to kind of confirm your suspicions. Next question. If an LTA system has an input of 3 to e to the -3t ut and an output of 3t u of -t, then what is the impulse response of the system? Okay. That is very weird. Um, I guess you could do this in multiple ways. And I will choose to do it in, I will choose to do it using Laplace transforms. Yeah, I will choose to do it in Laplace transforms. Or maybe let me think about it if it's a good idea. Yeah, I will do it in Laplace transforms. And so we realize that the Laplace transform of this is given to us. It's just 1 over s plus 3. And then the Laplace transform of this is given to us as, or maybe it's not a good idea. No, it is not actually. Hold on. Let me please think about this. I don't think it's actually a good idea. No, no, no. Or is it? Yeah, I'll do a Fourier transform way. I think it's Fourier transform is doing a better way. Chat. Previous problem, you shifted left by right because cosine of 10t. Yes, that is correct. For this, I'll take the Fourier transform method. And so I do take the Fourier transform of this function, which is something that we know. It's just 1 over 3 plus j omega. And the Fourier transform of this is a little more contrived, but realize that this is just the flipped. This is just, let's say this is x omega, x of t, then this is equal to just x of -t. It's just flipped. And so obtaining the Fourier transform of this flipped function is definitely easier. Remember the property that we have f of at will have the Fourier transform that is 1 over absolute value of a times minus a. We have this kind of thing. And so what happens is that x of -t will have the Fourier transform x of omega over -a, which is just, sorry, -1, which is just x of negative omega. And so we obtain 1 over 3 minus j omega. And so now all we need to do is realize that my output, my impulse response, h of t, has a Fourier transform h of omega, the frequency response, which is equal to y of omega, my output, divided by my input, which is equal to x, well, I guess I'll just write it out explicitly now. Which is equal to this, which is equal to this. And then from here, it gets a little, oh, hold on, I get a chat message. You do x of s divided by y. Yeah, I mean, I just chose not to do it because after you multiply the two, you have to kind of think about like causality. And I just didn't want to deal with that. Like whenever it talks about like region of convergence, it just gets a little annoying. So which is why I just chose not to do it. Um, anyways, but yeah, but doing Laplace transform is a completely valid method. So don't worry. So from here, we realize that this is 3 minus j omega plus 2 j omega over 3 j omega. And so this would be 1 plus 2 j omega over negative 3 j omega. I'm going to call again. Hold on. Sorry, I'm getting a call. Sorry, UCSD Fix It emailed me or called me. Um, how did I change e to the power of 3 ut to j? Okay, I changed that because I use this property right here, the like a time shifting property, and then I took a to be -1, and so that's how I took, and then that's how I found about y of omega, which is just the Fourier transform of this reflected signal, and so I could just get it directly from the Fourier transform of x of omega. Anyhow, let's just, I gotta keep crunching forward. What am I doing here? What am I doing here? Okay. And so I split into two. And now from here, it's probably not the most fun thing to do. So let me try to figure out how to make this look nice. Huh. Yeah, or maybe this isn't the way I want to decompose this. Oh, wait. I mean, yeah, pardon. Yeah, let me think about this for a second. What is the impulse response of the system? Um, let's see. 3j omega, and then I take that to the bottom. It's good. -at, that's good. And then I take that. Yeah, looks great so far. I'm trying to see if I made a mistake. So I do 1 plus 2j omega 3 minus j omega. I don't know. This doesn't look too nice to evaluate. That's the main issue that I have right now. Um, maybe if I keep simplifying, no. Huh. Trying to see if I could keep it at this. Um, huh. Um, hmm. Yeah, this isn't too nice. I'm trying to see time derivative property. But it worked out after some work. Use a time derivative property for this. Um, I guess you can, yeah, I mean, I guess you can do that. I'm trying to see if there's like a better, like nicer and easier way to make that final answer. Um, yeah, I don't know. I'm just trying to see if I can do anything here. Derivative times that, 2j omega. Yeah, I guess I can't really get rid of this. So, hold on. Is there a better way? I'm trying to see if there's a better way to do this. 3j omega. There's that. X of negative t. It's good. Good, good. Negative 3j omega. It's fine. Okay, okay, that's good. Yeah, I'm just trying to think about how to get out of this situation right here. Trying to see. Okay, I guess I will just try. No, there's no shot. Because I don't like to try to like brute force these questions because all these questions have or are kind of constructed in order to complete it in a certain amount of time. And so I'm trying to see if I could find anything. I guess I gotta suck it up and just do it on my own. So I will do so. Um, okay. And so if we take the Fourier transform of this, the inverse Fourier transform of this, then it becomes delta of t plus the inverse Fourier transform of 2j omega divided by this. And so I guess we're using the fact that j omega is right here. We use the property where g of t derivative will have the Fourier transform of j omega g omega. And so I claim to you that this is equal to the inverse Fourier transform of that is equal to the derivative of the inverse Fourier transform of 2 over 3 minus j omega. And so we obtain the derivative of time of 2 times e to the negative 3, but then it's reflected ut. And lastly, I just wrap it all up and realize that this is, I think I'm off by a factor here. 6 e to this 3t. I think I'm off by a negative here. Yeah, I'm off by a negative here. I'm trying to track down this negative. Negative 1 instead of what you did. Pardon? Hold on. The Laplace transform is easier to work with. I wouldn't necessarily say so. I would not necessarily say so. No. Or actually, maybe. I'd say it's worth working it out, but maybe not. Instead of what you did. What am I seeing here? Plus j omega. Wait, what do you mean by minus 1, 6? Oh, I see, I see, I see. Um, but well, before that, I'm trying to see if I made a mistake. Where did you get ddt from? Um, I used this for Fourier transform property, and I saw that j omega is sitting right here. And so I could convert this I could pull out this j omega that's sitting right here and and assume it to be the Fourier transform of a derivative. And so I made a pairing. Maybe I'll write it out fully. The derivative of 2 minus 3j will have a Fourier transform of j omega times, oh, sorry, I should do this. E to the negative 3t u of negative t. This has a Fourier transform of j omega times 1 over 3 minus j omega. And so, which is why I could take the derivative there. I'm trying to see 3 minus j omega. How did you turn that? This is just like a sum. Like I could split it to 2. It's like this numerator and this numerator are equal. I'm trying to see where I missed out on a negative sign. If anyone can see it, please let me know. Um, yeah, it's weird. It's weird. I'm trying to see where I'm going off. Um, Inverse transform 1 is that. What is the impulse response of the system? Yeah. Uh, I don't know. But I did get a comment. Hold on, chain rule. Where am I going down on? Well, where derivative u negative u delta 2t. Oh yeah. Oh, I forgot about the ut. Sorry. Thanks for that. Since I'm taking the derivative of this entire thing, I need to use the product rule because the derivative of this exists. And so when I do the product rule on this, maybe I'll leave that up. When I do the product rule on this, what I obtain is 6 e to the 3t u of negative t. Wait, chain, don't you mean product? I guess, no. I guess I leave it this and then multiply. No, I don't. Yeah, product rule. If I do product rule, then what I obtain is um, plus. Oh yeah, you're right. Negative 3t u of t. Oh, and I take the derivative of that, which is negative delta of negative t. So this product rule. Okay. And then I can realize that this product right here is just negative delta. And then I evaluate it at t equals 0. So this is just negative delta, or this 2 delta. And thus we obtain our final answer. That is a rough question. This is a rough question. There we go. Okay, thank you for the assistance there. But in the comments there was a comment saying, let me go find it. One way to do it is to convert this. I don't know, but it seems very contrived that you could even look for that. But you could rearrange this into the following form where you do this. And then, yeah, that seems very, very not easy to find. Or, I mean, I guess you can. Yeah, I guess you can find it. I don't think it's actually as easy. Um, I guess with the motivation, I guess you can do it. You can do it because you're doing it with the motivation such that you want to you want to make more constants. If you decompose it in this fashion, then what happens is you get another omega term, which is not very nice. So yeah, given a motivation that you don't want to make another omega term, you could convert this into negative 3 minus negative 3 plus j plus 6 over 3 minus j, and then you follow down into this part. And then this would lead you to the same answer. Yeah, that's a rough question. I'm I'm looking back and I don't know how I solved this when I took the class. But yeah, definitely a nice practice for working with derivatives, or you could just work with a lot of partial fraction stuff where you're decomposing it. Um, any questions? Questions, comments, concerns? I don't think it needs to be product rule. It needs to be product rule because we have two functions here. We have two functions that are in terms of t, and in the class in like our current class, u of t, even though it is discontinuous like this, we do have to consider the derivative of it, which is the impulse function, which is the delta function, centered at 0. Is that clear? Any questions? What happens to two? Oh, for this part, so if you're asking about this part, we're using the property where if I have some function times a delta function centered at 0, then this is just equal to the delta function, but multiplied by whatever the point on that point is. Questions? Okay. That was a long question, but I feel like it was a really good exercise to kind of bring everything together. Problem 13. What is the period of the function given right there? So when you analyze these kinds of ones, you want to see that you just want to get rid of whatever you don't need. So we get rid of that, and then we observe these two parts. This is a cosine. This is a function that has period pi over 8. And then we realize that this has a function that is period. Well, this is just precisely some constant times 2 cosine of 3t. And so this is period pi over 6. Hold on. Yeah. No, 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 no. This is not pi over. I don't know what the heck is up today. And this should be negative 3j pi over 2. Wait, what is up with me today? 2 pi, that's good. Yeah, this is period 2 pi over 2, and this has period pi over 6. No, this is period. Oh my goodness. This is not period pi over 6. This is period 2 over 3 pi. I'm so sorry, guys. I am not in my right mind today. But it doesn't really matter. So now all we need to observe is we kind of consider the number line, and then we see where these periods kind of line up. And so I will jump by pi over 2. And then I jump by 2 pi over 3, which is like around this much. Maybe not over there. Maybe it's more so like over here. And then we realize that both of them meet at 2 pi. So we found kind of like the least common multiple of both numbers. Essentially, that's what you're doing, especially when you're summing or taking a product of two periodic functions. You're just finding the least common multiple between the two periods. And we realize that the LCM of pi over 2 and 2 pi over 3 is just 2 pi. And so we get the answer 2 pi. Questions? Any questions? I got a question. So you always look for the multiple when the question asks for a period. Essentially, yes. So you want to break down, essentially, when you will be given, like usually you'll be given like a product or a sum of functions. And all you need to do is find the period of each individual term and then try to find the LCM across all of them. Anyways, I'm gonna keep on cooking until problem 18 and we can maybe take a break. The frequency response h of omega of the LTI system is that if a system has input x of t, which of the following is the output of the system? Okay. For this, you want to observe that h of omega, how would I put it? You use a duality here, where you use the fact that if f of t has an inverse transform f of omega, okay, then we want to see that f of t, like capital F of t, will have an inverse transform of 2 pi times f of a negative omega. And so what this means is that we know that what is it? I'm trying to see how to algebraically formulate this as nice as possible, but we see that this is f of omega is equal to negative, or maybe I'll correlate like this. This is equal to this, right? Then I could recover what my original f of t was, or my original f of omega, which is equal to negative 1 over pi plus 1 over pi cosine of 4 omega. We could get rid of the negative because cosine is a symmetric function, or is an even function. And then what this means is that we could kind of change the name and just call this f of t, just changing the name of the variable. And we realize that this means that f of omega is equal to negative 1 over pi. I think it's actually negative 2 delta of t plus 1 over pi. So 1 over pi, and then the Fourier transform of that. So this is the Fourier transform. Pi cos delta omega minus 4 plus pi delta omega plus 4. And this is equal to negative 2 delta t plus this plus this. Voila. Question. Oh yeah, you could do that too. I mean, I feel like I got a comment. It'll break down convolute with a bunch of deltas. Yeah. I'm just choosing this method because it kind of uses this. Um, but actually I'll solve this in a different method as well, just because why not? Um, and so let's see here. And so now that we recovered f of omega, um, this must mean that when we put x of t into our system, our output is x of t convolved with f of t, capital F of t. Remember, this is because this is my impulse response. Or sorry, this is my h of omega. And so basically when I do this convolution, I basically obtain the desired answer. Voila. And that's it. Of course, in my opinion, that was actually kind of a more complex method. Or no, I want to say complex, but if you know this property, it's convenient. Another way you could do it is to realize that your output is equal to obviously the input, but then h omega is just a sum of exponentials. 2 pi, no, sorry, 2 e to the, actually, no, it's just normal. E to the 4 jt plus e to the negative 4 jt times x omega. And in fact, it is not t, it should be omega. I don't know what the heck I wrote there. And then if you expand this sum, you get something like this. And then you realize that each of these has a very nice Fourier transform, inverse Fourier transform that you already know. This is a modulation in frequency, so therefore it's just a shift in time. This corresponds to, I don't want to get this wrong, so it's t minus 4, I believe. No, it should be t plus 4. Yeah. And then the second one is t minus 4. And it gives you the same answer. So I guess this method is way easier, but it's good to have exposure to the both ways to get to the final answer. Let's keep going. Yeah. What is the convolution of, or h of t is a convolution of f of t and g of t? What is h of 3? This is by no means, or by all means, a time convolution question, my favorite, because I get to draw graphs. And so I will probably proceed to do so. We know that the integral that we want to evaluate is f of t, f of tau, g of 3 minus tau. Of course, you can switch whichever way you want, but I'm going to do this way. My red function, I'll actually draw it right on top of here. I will draw g of 3 minus tau right on top of this graph. And so what I do know is that we know that g of negative tau will look something like this. Then g of 3 minus tau will look where we pull this center to 3. And so we basically translate our function flipped function to that point. There we go. So this is g of 3 minus tau. And now all we need to do is take the product, right? So let's take the product. I want to graph the following function, f of tau times g of 3 minus tau over tau. Well, it's going to be 0 for all these numbers, very clearly. It's going to jump up to 2 times 2, which is 4, for 1. And then it's going to drop down to 2 times 1, which is 2. That is not drawn to scale, but I don't care. And then lastly, it's going to drop down to 1 times 1, which is just 1. And that is our graph. I hate the fact that I didn't draw it to scale, but it's okay. And then we realize that it's just 1, 2, 3, 4, 5, 6, 7. So the integral of that is just 7. Boom. That easy. Question. Could you please scroll up for the final part of Q14? Sure. Wait, how did you do that? Yeah. So when you're doing convolutions in time, it's very important to evaluate the product of the functions correctly. So after Q14 is done, I'm going to scroll down to Q15. So when I take this product, so I'm assuming that most of the confusion comes from where do I get this purple function? Well, let's chop it up into pieces and examine it. Or maybe it's better to highlight. I am examining everything over here. That corresponds to the product of the functions over here. If I take the product of the red function and the blue function in the blue region, then f of tau times g of 3 minus tau is just equal to 0. Everything on that side. Why? Because the red function is 0. And if you take the product between a function that is 0 and a function that is not 0, it's just going to be 0 anyway. Now let's consider this area, because this area is probably the most confusing. In this area, we have f of tau is equal to 2, confirm right here. And then we have g of 3 minus tau to be also equal to 2, confirm right here. Let me actually maybe highlight in purple why that is. That is not a highlighter. That is blue. I have this part corresponding to the product of those two things. I'm taking a product. When tau is between these 2 points, 0 and 1, f of tau is 2, and g of 3 minus tau is 2. Therefore, 2 times 2 is 4, so I get 4. And I do the same exact thing for the interval right between here. That is not 0 and 1, that's 1 and 2. Between 1 and 2, I realize that uh, if tau is between 1 and 2, I realize that f of tau is, well, it's 2. And g of 3 minus tau is equal to 1. And thus, I get 2 over here. And I could proceed and draw out the entire graph in the same fashion. You're taking the area of the over. Yes, every single time I'm just like, whenever it is like a convolution in time, every single time I'm just taking the area of the overlapping, like, okay, sorry. I first take the product of the two functions. And when you take the product of the two functions, you're basically taking it pointwise. Why'd you make g of t into g of t minus t and not f of t? It was just my choice. In reality, it really doesn't matter. It'll give you the same answer. It'll give you the same 7. I just chose g of 3 minus t. But otherwise, so basically what you do is step 1, you formulate this. Step 2, you just find whatever this function looks like, this product of these two functions. So you first draw f of tau, which is your red. And then you draw out g of 3 minus tau, which is in the blue. And then you just take the direct product between the two functions. And when you take the product, essentially what you do, like this is probably the biggest part that confuses many people, but when you take the product of two functions, all you do is you at any particular point, you say, oh, what is this point? What is this point? Okay, I multiply those two, and then I get uh something like, and then I just take the product of those 2 points at that particular tau, and I just take it at that point. Like that's it. That's when I take product of 2 points, two functions. If the answers were in terms of u of t, what would it look like? I do not want to do that. I'm sorry. Um, that would, like, yes, you could do it, but you're gonna have to shuffle around a lot of. Oh, I mean, eh, it'll be okay. Like f of t would be equal to, if you really insist, then it would be this. As a side note, because this would actually waste a lot of time. Like if you do this in exam, it'll be very time consuming. Um, so I don't recommend this, but if you were to write it out as a unit step, sum of unit step functions, you get something like this. Boom, boom, boom. There we go. And then you take the product of those two, uh, and like algebraically speaking, taking the product of these two is not going to be very fun. I will 100% assure you. But once you take the product, you would just obtain like 4 ut plus 2 u minus 2 ut minus 1 plus, no, minus ut minus 1 minus ut minus 3. I don't know. I don't recommend doing it in unit step functions. It's not very fun. Do you shift first, then flip? Because g of t minus 3 will be shifted left, right? You flip first, then shift. See here, I flipped first, then shifted. But if you like to shift first, then flip, like be my guest, it doesn't really matter as long as you get the right graph at the end of the day. Okay? Again, I'm sure there's another time convolution question, so we can get more practice from that later. But otherwise, it's very important that you understand how to take product of two functions point-wise. You just go point by point. All you're doing is you go point by point and you say, oh, what is the value of this point? What is the value of this point? Oh, it's 2 times 2. Oh, sorry. Along this line, what is the value of the red function and the blue function? And I say, oh, it's 2 times 2, which is 4. And I get 4. That's it. I'm just going down the line and seeing what value I get as I kind of like change tau, and that's it. Anyways, if there are more questions, I'll be happy to elaborate, but it's been 2 hours and 12 minutes, so I would like to get through half the exam and then finish off before 12 maybe, because people need to sleep. Otherwise, um, which of the following 4 time signals are band limited? Okay, so let's take a look at this. If I reorganize this, this is sine of 2t over, sorry, sine 2t squared, and I'll say 4 times t squared times 4 so that I preserve my t squared. And I have another sine function, and I have another cosine function. Okay? And hold on, let me see if I'm doing this correctly. Yeah. Okay. So with this, we realize that this is a sinc function, and then we have a periodic function right here. Periodic functions are band limited. The Fourier transform of this is a rect function, which is band limited. And so I'm if I the product of these two, so I put these together, the product will yield a convolution of a rect and some deltas. You don't need to write out anything. All I'm just saying is that conceptually speaking, if I were to take the Fourier transform of this, then it would be, since I'm taking a Fourier transform of a product, I would be in the frequency domain, I'd be considering the convolution of the Fourier transforms. And since this is periodic, I would be convolving some deltas. In fact, like this is most definitely band limited because it's a product of sine and cosines. And so this would yield a finite number of deltas. Let me make sure to clarify that. And then rect functions. So if I add these two functions, sorry, if I multiply these two functions in time, then I'm taking the convolution in frequency. Yeah, so the Fourier transform of a v of t will look something like a convolution of a rect function and some deltas, which is most definitely band limited. And I'd be happy to draw it out, but it's important for you to see that, like, it's important for you to convince yourself that this is true without just explicitly drawing it out. And try to think about it, right? Um, essentially what I did was I broke this function down into a part such that the Fourier transform is a rect function, and I broke it down to another part where it's a finite number of, like it's a sum of probably like n equals 1 through 4 of some deltas. I don't know what deltas it is, but it's going to be some deltas spread out, and it's going to be like 4 of them, maybe 5. If I convolve a rect function with some deltas, then very obviously my Fourier transform my convolution will just be a bunch of copies of my rect functions, and you could definitely band limit that from the outside. Are there any questions? Does anyone would like me to clarify what my thought process here is? Because like for these types of questions, there is 100% not enough time for you to find the Fourier transform of each and every single function and then consider if it's band limited or not. It is imperative that you have the intuition to kind of make these deductions based on what you know. So if anyone would like me to clarify, I'd be happy to do so. So please speak out. But otherwise, I'm going to consider each and every other one in the same fashion. Question: what makes a function band limited? A function is band limited. X of t, I'll use an A of t is band limited if the Fourier transform A of omega fits inside a nice box. Like it's beyond some negative omega, maybe I'll say a number, between some negative b and b. The entire Fourier transform spectrum lies inside it, like is non-zero inside it, and everywhere outside of that is just zero. And so if I visualize this particular one, I'll do it later, but I'm going to do the same thing over and over again. So maybe you'll see some practice and patterns. So let's think about x of omega. X of omega is clearly a convolution between the Fourier transform of a rect function and some deltas. Up to constant, right? Like, I will write down the constant. Plus pi, boom, okay? And the Fourier transform of rect is not band limited. If I take this convolution, I'm placing two copies of non-band limited, of a non-band limited signal. So this is two copies of non-band limited, that's a long word, signal. And so you could automatically deduce that this is not band limited. My hand hurts from writing band limited. I will just copy it. Thus, we could deduce that this says that x omega is not band limited. All right, consider y of omega. Y of omega is equal to rect t squared. What is this? This is just rect of t. And what is the Fourier transform of this? It's a sinc function of some, like up to some constant. Like it's similar to, here I'll say this, it's proportional to the sinc function. I feel like there's like a 2 somewhere. Maybe it's like t over 2. Whatever. It's similar enough to a sinc function. And a sinc function, what in the world? Oh, my Zoom crashed. Oh, hold on. I think my tablet's reconnecting. Ha. Let me kill Zoom and then try to rejoin. Anyways, are there any questions like so far on what I'm doing? I'm like very happy. I'd be very happy to clarify um like which parts that doesn't make sense because the intuition on these band limited things will actually go a very long way. And so please speak out. Let me just make sure to rejoin the Zoom. There we go. Okay. What is going on? Okay, there we go. And so we know that the y of omega will have a Fourier transform that looks, what in the world am I drawing? Y of t is equal to rect t, then y of omega will look like something like the sinc function. And so this must mean that this is not band limited either. Lastly, let's take a look at z of t, which is sine to the 4t plus cosine to the 4 of t. And this is periodic with max frequency. I mean, it's hard to kind of pinpoint. So there's a bunch of ways to think about this, and I don't want to fixate how you guys think. So I will present one way, but you're free to think however you want. Um, and the way I'll do this is I'll observe that sine of t has a Fourier transform of like some like a constant delta somewhere. So sine is as a Fourier transform of, I'll just write it out, I guess. 1 minus delta A1. There we go. And then essentially what I do is, um, what is it? What am I doing here? If I take this to the power of 4, what I'm doing is I'm convolving this thing, then the Fourier transform of this, let's call it z1 of omega. This will be proportional. Let me proportional, or at least similar to, to a bunch of deltas convolve with each other. And now I want you to imagine, everyone just imagine, do not evaluate this, please do not, but imagine you're convolving a bunch of deltas together, a finite number too. Then wouldn't your final product of all the convolutions just be a bunch of other deltas? I really hope you convince yourself on this. This is just another, like, just a bunch of deltas. I'll just literally just write bunch of delta functions of like, I don't know, just a bunch of deltas. I want you to convince yourself on this. If you convolve a bunch of deltas together, and assuming that the number of deltas is finite, then your final product must be just another bunch of deltas. And so with this kind of intuition, you could realize that this is just also band limited because the deltas only can go so far. Remember, they're finite. You're a finite number. And so you'll have something like this. Oh my goodness. You'll have something like this. And I actually don't know how many you have. Maybe I think it's around like 4 or 8. And then you realize that, oh, I could just kind of wrap it around in this box. And that's it. You're done. So you realize that this is, oh, I don't know why I copied around that, but this is band limited. And so realize that X and Y are not band limited, but V and T are, hence we have this. Any questions? Remember, please ask questions because this question in particular is one of those questions where you have to think quickly and your fundamentals need to be strong in order for you to solve it within the time constraint. And trust me, this problem is not in particular like arithmetically hard. But if you choose to take the Fourier transform, of course, it will be arithmetically hard. But with strong intuition, you could skip all the steps and solve it like this. But you know, I'd be happy to come back to this. But I'll move on for now. Oh my God. The real and imaginary parts of the Fourier transform of the signals f of t and g of t are shown below. If the convolution of these two time signals, z of t, is f convolved with g, what is the Fourier transform of z omega at omega equals 1? Oh, it's actually not that bad. Um, then we know that z of omega, or in fact, z of 1 is literally just f of 1 times g of 1, which is equal to, we're basically going to cherry pick numbers. F of 1 is equal to 1 plus j. Let's just say, combine these two to get f of 1 is equal to 1 plus j. And then we're going to combine these 2 points to obtain that g of 1 is equal to 1 plus 2j. I guess it was initially very daunting at first, but you know, it's not that bad. Then we get 1 plus j plus 2j minus 2, which is 3j minus 1. And that's our answer. Voila. Not too shabby. Um, and then 17. I believe that's 17 and 18. Okay, we're gonna do 18. Actually, yeah, we're gonna do 18. I'm gonna take a short break. So if the impulse response of a linear time invariant system is e to the negative t ut, then what is the system's output when the input is also e to the negative ut? So I'll be completely honest. Oh, question. For v of t, can you analyze the Fourier transform of sine and cosine since you're just multiplying deltas, you're getting back the value of delta of the series problem? Mm, no. And actually, no, not necessarily. The only issue with that is this bottom t squared. The question is, how can you deal with the bottom t squared? And so the sine and cosine is not like the multiplication of sine and cosine is not enough to tell you that it is going to be band limited. You have to manipulate it so that you get something that's very definitely band limited, which is a sinc function. And then you have to multiply, and you have to realize that the leftovers are a bunch of deltas. But that's a good approach though. Like that is good intuition though, of thinking how sine and cosine can be um, somehow they have a strong impact towards band limitedness. Anyways, so for this
Can
question,
you
it's
go back
very
to
it's what's your question?
can you go
Question,
back to
yes.
problem 17 for just 1 second?
Oh yeah, of course.
Okay, awesome. Thank you.
Okay. And then so for this question, the very interesting thing is that I recall the professor literally made a formula for this, but you don't need to do that. All you need to do is realize that I guess you could do two different things. Um, hmm. I think what I want to do here. Um, yeah. So there's a lot of ways to solve this question, but I'm gonna do one particular way where I will take the Fourier transform of e of to the power of negative t, ut, which has the Fourier transform 1 plus j omega, and then this will also be 1 plus j omega. And so my output Fourier transform in the frequency domain will be 1 over 1 plus j omega squared. And I guess actually this is not very easy to compute. Huh. Maybe I'll leave this out. Maybe I will not do that. And instead I will do this. I will convolve it in time. And so I will evaluate the convolution between e to the negative tau u tau and e to the negative t minus tau u of t minus tau d tau. And the reason why this is not bad is precisely because we have unit step functions right here and here that make the um, integral actually rather not too hard to solve. And so what I want to do here is we could use these two to kill the bounds. U of tau is 0 when tau is less than 0, and 1 if tau is greater than 0. U of t minus tau is 1 if tau is less than t, and 0 if tau is greater than t. And so what this means is that if you are less than 0 or greater than t, then you kill off the bounds. And so we realize that you could kill off the bounds to just become 0 to t, e to the negative t times e to the negative t minus tau. Does everyone see how I could like evaluate or like get rid of the integral bounds using the unit step functions? So using these two, I could eliminate the integral bounds. And now we realize that this integral is actually not too bad to solve. First of all, we realize that we're actually integrating by d tau. And so if I could actually pull out, or maybe I could maybe make it easier first, e to the negative t. Uh, hold on, tau, which is equal to, oh, sorry. It's just, and it's very easy to get fooled, but remember, we're integrating by tau, which means that t is a constant here. And so I could pull this out, and we get this, and now this integral is just equal to, this is just equal to t. And so we obtain, well, okay, I'm gonna have to elaborate a little more. Hold on. Um, let me just write this out first. Huh. I guess I have to elaborate. So your decision kind of splits over here, where let's say that let's say you choose a t that is less than 0, okay? Of question. I don't understand mathematically why it needs to be multiplied by u of t. Yeah, so I'm gonna get to that part. Um, let's say that, so the u of t comes from the fact that right over here, comes right over here, or more so right over here. Doesn't really matter, actually. Um, consider the product of these two. And this is actually very interesting. I feel like it's one of the best parts of this class. But if you choose a t less than 0, then and graph out my two unit step functions, then we realize that for any t less than 0, we have u of t minus tau to have no overlap with the unit step functions, with other unit step function. So we realize that, or it's imperative to realize that the case is split into two, which is um, if, so actually, I guess I should have been a little more attentive to details, but if t is greater than 0, then you can get this integral because this is 1 and this is 1, so you get 1. But if t is less than 0, then you just get that this integral is equal to 0. Does that clarify why that is? Yes, yeah, so it's that's the part I kind of missed out, but it's very important to kind of examine this. So you realize that our function or convolution is t e to the negative t when t is greater than 0 and 0 else. And so we could obtain that is just t e to the negative t u of t. But also I think he derived this in class. So if you have that on cheat sheet, that's a free question. But I'm solving this is also not too bad. Anyways, that's problem 18. So I would like to take a short break. Um, it's been 2 hours and 35 minutes. But I will go through this entire final, no matter what. But please take a short break, and I'll be around here just to like answer questions. So if you have any questions regarding previous problems, I'd be happy to answer them right now. To go back. But yeah, I'll restart back at 10:40. Charge my laptop too while I'm at it. The review session for 22 was not posted yet. I'll actually post that right now. Thank you for reminding me. Yeah, so I'll post that right now. Thank you. Let me, recording is here. Shareable link, and then no passcode. Right, voila. And so I will post it. Link. There we go. All right, I have updated it. Okay, let's get right back into it. So, part 2, another 18 questions. Whew, I recall that part 2 was significantly easier than part 1. And so hopefully that this will not be too bad. Anyways, which of the following has appeared as a Fourier series? So this means that must be periodic. And so let's see which ones are periodic, which ones are not. So very easily we could eliminate a bunch of these. Boom. Those are already all killed off because periodic. And the only control, like the only slightly harder ones are these 3. Well, I don't want to cross it, I want to underline it. And well, let's take a look at all of them. Sine of t squared. Well, the only issue with this is that you are, if you, oh, my Zoom died again, I think. Or not. Yeah, my Zoom died. I don't know how my stream is still going. What in the world? Um, that is so weird. Yeah. Hold on. Let me rejoin. Sorry about that. Why is this crashing so often? I don't know. Sorry, guys. My Wi-Fi network is very slow on my tablet for some reason, so it's just taking a while. How is sine of t squared period? Oh, it's not. It's not periodic. I'm trying to show that it is not. How did you automatically eliminate those just by looking at them? I will elaborate. Let me just join. Dude, like I don't know why this is so slow. It's just not joining. That is so not epic. Uh, I guess it's the finals week Wi-Fi right now. Let me try leaving rejoining again. I don't get it, man. This thing is not very responsive. Okay, there we go. Just join the meeting. Please, 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 please. It's just joining. Like, sorry for the delay, guys. I'm just gonna be sitting here until my tablet loads, till it joins. Yeah, I don't know. I don't know. It's just taking a while. Um, let's see. Let me see if I could connect to a different network. Oh, my phone is about to die. FIB2G. There we go. Okay, I connected to a different Wi-Fi, so hopefully this one's a little faster. Let's go. Okay. We're back in business. All right. So, first question, how did I know how to get rid of a bunch of these functions? Well, all the black ones, we can see that they're just not periodic. Like just like straight off the bat. Because we have a non-periodic term. We have t at the denominator, we have t at the denominator, rect function is not periodic. E to the 2t, that's an exponential function that's not periodic. Like, I'll actually draw all the functions. This will look like this. This will also look like this, or something like that. E to the 2t is exponential. U of t looks like this. Delta t looks like this. E to the that looks like this, I believe. And now, like just examining straight up um how the functions will look like, they're clearly not periodic. Hence, they will not admit a Fourier series. Now, the second question, are these periodic? Are the ones that I underlined in red? Well, let's actually take a look. Think about what sine of t squared would look like. First of all, if I, it would just be a normal sine function, but my argument is increasing faster and faster. And so if I visualize what sine of t squared would look like, it would look something like this. It would look like normal sine, but then it get faster and faster and faster and faster and faster. Obviously, the amplitude should stay the same, so maybe I'm going to redraw it. And there we go, it's just aperiodic. So it's not periodic. For this, sine has period 2 pi. Cosine of pi t has period cosine pi t has period 2. And now I want to ask you, well, can you find me a nice least common multiple of both numbers? So does there exist? Can we have m times 2 pi equal to 2 times n for mn integers? That's exactly what I'm asking you. Like, this is what I'm asking when is there a least common multiple? And the answer is just no. Why? Because one of them has period that's irrational. What happens when t equals pi for this one? For which one? Which t equals pi? Yushan, can you specify like what do you mean by when t equals pi? Sine of cosine of pi t. Regardless, even if it's uh yeah, like when t equals pi, then it'd be sine of pi. Like I don't see this won't tell us anything. Like what do you mean by this? I don't I'm not, I can't particularly see like what do you mean t equals pi? How will that help us prove periodicity? Um like you mean the period or okay. I'm gonna keep on going, but I'll like look out for the follow-up comment. But essentially, for these two functions, we basically break it down into each individual term and consider their periods. And then what we do, oh, okay. And then what we do is we check, okay, can this sum ever be periodic? And we check if the LCM of, or for example, can we have m times t1 equal to n times t2, where mn are integers? And the answer is no, because one of them is irrational. I feel like this was covered. This was like there's a lot of practice on determining periodic functions in like lectures 2, I think 3 and 4. And this is exactly that, where you find the period of each of the two terms, and then you see can the sum of them ever be periodic, and to do so, you just try to examine the least common multiple between the two numbers and see if there exists integers such that they'll kind of line up with each other. Anyways, and then so this tells us that B and J are no longer periodic, and thus, right, so doesn't that go for multiplication too? Yes, it calls for multiplication too. So hence our answer will be A. This is about a process by elimination. Uh, yeah. Okay. I'd be happy to come back to this question and elaborate on the intuition, but we are very far behind schedule, so I'd like to kind of speed through the rest. What is the impedance of a 200 inductor when the frequency of the sinusoidal current through the inductor is omega equals 2? Um, okay, this is j omega L, and this would be just 4j is equal to 4e to the e power over 2. That's a very clean question. Nothing too complicated. Suppose two linear time invariant systems are cascaded as shown below. The first system has an impulse response of that, and the second produces a derivative of its input as its output. If x of t is u of t minus 1 plus minus u of t plus 1, then what is the output y of t of the cascaded system? Okay. This doesn't look like a very fun question in my opinion, but it's okay. So here, it's important to observe that x of t, I guess you could just leave it as follows, but we're putting this, let's say this has impulse response h1 and h2, then we're basically considering the output like that. But then here, um, we remember that convolution is commutative. So we could swap the order at which we convolve. And then now we know that x of t convolved with h of t is putting into this system. So x of t put into system 2 will give us a derivative of x of t. And assumably that is actually rather easy for us. this will just give us delta of t minus 1 minus delta of t plus 1. Or maybe I will do this. I will write it coherently first. And then I will write down delta of t minus 1 minus delta of t plus 1 convolved with h of t. Okay. Hold on. I want to make sure that I'm doing this right. Hold on. Impulse response of that. I think I am fine. Yes. Okay. Though, yeah, I think I'm doing fine. And afterwards, we realize that now this is just a convolution between um, delta functions and unit step functions. And so, I mean, it's just a function and the convolution between deltas. And so I could just do this. And then I could end up with just deducing the final answer. E to the negative pi j t minus 1 over 2 minus e to the negative pi j t minus 1 t plus 1 over 2. And then I would just expand this. We have e to the negative pi j t over 2, e to the pi j over 2 minus e to the negative pi j t over 2, e to the negative pi jt negative pi j over 2. And then we realize that this is just j. This is just negative j. And so we obtain that this is 2j e to the negative pi jt over 2. And our answer. Well, there's a question. I tried doing it, making x of t, right, and got lost. That, I mean, I feel like the if you so I got a comment saying, okay, I could convert x of t to be rect of negative rect of t over 2. That is, I don't think that's actually that is right. And from here, you can do two things. Let's say you do this first, right? So what you can do is you could convert e to the j, I keep forgetting what it was, negative pi jt over 2. So alternatively, negative pi jt over 2. You could convert this, and the inverse transform of this is actually it's actually not too bad. It is just, what do you call it? It's just a shift in time. It's just a shift in frequency. This is actually just delta of omega plus pi over 2, if I recall. Let me just make sure that's right. JYT. Yeah, this seems right. And so with this, there's another question. How'd you go from that to that? Okay. Um, so given this, you could actually just now evaluate this, take this into Fourier, and then bring back to time, and then back to time. And then let's say you get z of t. And then now you just convolve it with h2 of t, which should give you the same answer. Like that'll be the process. I'm sure, I think you made a small mistake on probably like, I think that the hardest part was to think about how to evaluate this part, but you could just take it to the Fourier domain, which is not too bad since you have a sinc function. Another question. So how do you sum from that to sum of deltas? Um, this derivative of this is equal to this. And then I obtained that because I know x of t is a bunch of unit step functions. Anyways, moving on. I'd be happy to come back, but I'll try to speed through. What is the Fourier transform of the convolution of those two? So we want to take the Fourier transform of that. Well, all we need to do is take the Fourier transform of the individual this is 1 over 1 plus j omega. And then we realize that the Fourier transform, your answer is just equal to the product of these two. So your answer, I don't know how to write. I just don't want to write out the functions again, but I'll just write it out anyway. This is equal to the product of the convolutions. And if people remember their delta function properties, where if you multiply a function by the delta, then what you do is you just evaluate it at that point. So let me actually distribute this first. And then since I'm multiplying this function by a delta and located at 2, I just evaluate this function at 2. And then for this one, I just evaluate the function at -2. And thus I obtain my answer. Okay. Oh, this is plus. But yeah, so nothing too shabby here. I'm gonna keep moving. We have a bunch of problems left. A particular system's input x of t and y of t satisfies the following differential equation. What is the output signal when the input signal is delta of t? And so what this should be a very high highlight that you're basically finding the impulse response of the system. And so let's do that. So observe this system. Let's actually take the Fourier transform on both sides. Or, I mean, you can take the Laplace transform. It's really whatever. I'm going to take the Fourier transform because that's actually, I guess it doesn't really matter. I will do the Fourier transform personally. So I will take the Fourier transform on both sides. And I will take the Laplace transform. Sorry, I'm changing my mind constantly. Yeah, sorry about that. So if I take the Laplace transform, then by Laplace, the Laplace transform of both sides must be exactly the same. So, please note that. And so, what we note is this will be s squared of ys plus 5. I mean, there's an intricacy here, but I'm going to skip over it because we will not worry about it too much. Is equal to s xs plus 2xs. And so we could organize ourselves to see that y of s over x of s is equal to s plus 2 over, I forgot the 6 here, s squared plus 5s plus 6. This is equal to s plus 2 divided by s plus 2, s plus 3, 1 over x plus 3. And we realize that this is actually our frequency response. And so this should yield our h of t, which is equal to the output of when you insert delta of t. And so, and this is equal to the inverse transform of 1 over s plus 3, which is e to the negative 3t u of t. And there's our answer. Questions? And if the anti-causal case were an option, would it be a valid answer? Mm, great question. Um, I will say yes for now. The only thing I would have to like strongly consider is like the interaction with causality and differential equations. Yeah, because differential equations is kind of like a thing where you it just feels counterintuitive if you consider anti-causal, but I think it would generalize well. So I think yes. But I don't think that we would be evil enough to give you two conflicting answer choices where we never clarified a what do you call it? Where we never really clarified this kind of intricacy. That would not be very cool. Anyways, that's that question. Got a question actually. Doesn't make a difference in convolve with delta t at the end, right? Um, yeah, actually, yeah. So, um, what I do think is, I mean, it can make a difference. I believe it can make a difference. Because from here, you could take the anti-causal inverse transform and then obtain a different answer for over here, which is exactly why. I don't think, like, it does matter, but we will not give you the answer choices that would be conflicting like that. Anyways, if x of t is a sequence of a bunch of delta functions, and x of omega is the Fourier transform for x of t, then what is this? So it suffices to just find x of omega, which is, well, it's a bunch of different things. Didn't we do this question? I feel like this is a past. I already did this question. It's like deja vu. This is sum of delta of t minus 1 minus 2n. And so we realize that this is a shifted signal. So x of omega would be equal to e to the, I keep forgetting where this goes, but I believe it's just j omega times the Fourier transform of the sum of the impulse train. So essentially what I did was I got rid of the minus one by pulling it out and saying it's modulation in frequency. Like I essentially used the fact that a shift in time is a modulation in frequency. That's all I did. From here, um, actually, let's think about the magnitude already. If I think about this magnitude, then I could think about the product of that, and then I uh think about hold on, this is actually rather not cool. Um, this is magnitude of this yields period is 2, which implies that omega naught equals pi. And so this is a sum of delta functions that are, right, pi times delta functions that are spaced out by pi. There we go. So this is what we have so far. And then now we realize that this is equal to, well, this is equal to 1. And then we could pull out a pi. And then all we have left is the magnitude of a bunch of impulses. And now let's consider this integral. Well, if I graph out my function, then uh, if I graph out my function, I'm integrating from 1 to 7, and I want to consider how many delta functions fall into that interval. And we realize that only two delta functions fall into where I'm integrating. And so this means that this integral evaluates just 2. And thus, our final answer is 2 times pi. Questions? Comments, concerns? It's 11:10. I think we're going to be okay. I'm just going to keep powering through. Remember, I'm going to be sticking around for after office hours, so please feel free to ask questions then or even now. Which of the following is not a periodic function? None of these questions again. Let's take a look. Um, so it's easy to get rid of a few. Like, okay, how do I put this? So this is one of the things where you just have to look at each and every single one and realize that it is periodic or not. And here are the general rules. If f is periodic and g is periodic, then f composed with g of t is periodic, f plus g is periodic, and f times g is periodic. In fact, f to the power of g is also periodic. All these things are periodic. In fact, um, for the following, if g is periodic, it, sorry, let me make this in general. This is periodic. If only g is periodic, then f to the power of g, t is periodic, and um, f composed with g is periodic. These are just, maybe you want to write this down, but this will come in handy in this particular question. And so we realize that this is periodic. This is a train of rect functions spaced out evenly. This is a rect. I'll just call it a rect train. And thus it's periodic. This is a periodic function that is embedded in another periodic function. This is periodic. Similarly, this is also periodic because this is a periodic function. This is a periodic function. This is also a periodic function. This is a periodic function. This is a periodic function. This is a periodic function. These are all just periodic. Like, if any one particular one of these confuses you on why it's periodic or not, I'd be happy to clarify. Um, but mostly by inspection and using these rules, you could kind of knock all these out. And the only issue is this little boy, where we have this absolute value of t of sine. And if we already examine it, just a component of it, this will yield a graph that looks like this. And I'm sure this example you've probably seen this example multiple times, but it'll look like something like this. And that is clearly not periodic. You'll never get this like this little dip, this little cusp anywhere else on the graph. And so because this is aperiodic, this is aperiodic. And so this is our final answer. I'm gonna move on for now, but I'd be happy to come back and just re-elaborate on things. Just please note, just because we're on the time constraint. What is the bilateral Laplace transform of u of t plus e to the power of t times u of negative t in this region of convergence? So this, we just take the Laplace transform of each individual one. We get that this is 1 over, 1 over S, and its ROC is real part of S greater than 0. Let's actually draw it out. Is S greater than 0? This yields a S S minus, hold on. I believe it's S minus 1. And then we have the region of convergence to be S less than 1. And so we could draw out these two lines. And then we take all this, right? Maybe I just want to highlight it. And so we realize that our Laplace transform is equal to 1 over S plus S minus 1, 1 over S minus 1, which is S minus 1 plus S over, hold on. So it's just, I think I made a mistake here. Periodic G, hold on, I got a question. If F is periodic and G is periodic, can you say that F? Oh yeah. Sorry, I have to clarify that. Hold on. Let me go back. Let me go back on that. But let me just finish this. So S minus 1, S plus, I think I made a typo somewhere here. Or perhaps not. U of t, e to the t, u of t, S minus 1, that's good. Oh, then this is minus. Yeah, because I have that negative e to the t has a Laplace transform of 1 over s plus a. And so, sorry, at has s plus a. Therefore, I have to take the negative of this. And so, therefore, I would do this, and then this would be s squared minus s, which is equal to negative 1 over s squared minus s, which is equal to 1 over s minus s squared. And we take the answer choice with our correct Laplace transform and the region of convergence that matches our answer. I have to go back. I have to go back up because I straight up misinformed. Hold on. Okay, yeah, thank you. But for this, I completely forgot. But for these two, G periodic and the LCM of the period. So let's say TG, let's say this has period of TF, and let's say this has a period of TG, then we want there exists, or TF divided by TG is rational. Then you could claim that these two are periodic, but otherwise, no, it is not periodic. So this is, sorry, I'm very sorry about not elaborating on that. But for this one, it definitely holds. Yeah, this one it definitely holds. Anywho, uh, yeah, perfect. Thank you very much. Thank you very much for the corrections. But yeah, so and then we would get this kind of answer. Next question. Problem 27. Suppose the LTI system has frequency response of 2 plus j omega divided by 3 plus j omega, and the input to the system is a periodic function of the Fourier series shown below. If the Fourier series of the output is that, then what is the magnitude of y1? Okay. So I think for this particular question, again, you could do it two different ways. But using the LTI system property, you realize that y1 e to the negative j 4jt. So this is the y1 component, right? If you could kind of extract the n equals 1 case of this and then extract that. And if you put this into the system, sorry. of this, you obtain the n equals 1 case of this, and you get 1/2 e to the negative 4jt, okay? Then what we can observe is that if I put this into my system, then what I obtain should just exactly be h omega e to the j omega. And why is this? Well, it's the eigenfunction property. I gotta comment. Oh yeah, 1 second, the periodic stuff. Yeah, of course. Okay, right. I'm just gonna go past. Anyways, so because of the eigenfunction property, we know that if I put in this particular component, the n minus 1 case, then I should recover the exact same thing, but multiplied by when omega is equal to whatever this is. This is 4. Remember, because I'm putting in negative 4jt, sorry, I should get out 1/2 h of negative 4 times e to the negative 4jt. This is very important. This is the eigenfunction property. And so all I need to do is now just evaluate this. Well, this is 1/2 2 plus 2 minus 4j, 3 minus 4j, e to the negative 4j. And now all I need to do is realize that this is my y1 now. And now I just need to take the magnitude of y1, which is equal to um, the magnitude of 1 minus 2j over 3 plus minus 4j. This is the magnitude of that divided by the magnitude of that. And then the numerator is just a 1/2 triangle, 1/2 right triangle, and the hypotenuse of that, which is square root of 5. Denominator is just 3/4 triangle. Take the hypotenuse and you get just 5. And so you get this. Next question. I'm just gonna keep on flying by, but if you have to ask a question, I'll happily go back. If the Fourier transform of f of t is f omega, then what is the Fourier transform of that? So we have this. And now by linearity, we could take the Fourier transform of this individually and realize that we have the property where the Fourier transform of this is equal to j times the derivative of f omega. This is a property proved in class. Like it's something that was mentioned in I think week 4 or 5. And so with this property, you could just directly deduce that your answer is this. You have a Fourier transform property, and so yeah. Anywho, problem 29. For each input x of t, a system creates an output e to the x of t. Which of the following properties must the system have? Gut reaction. This is not linear, and I will literally just show you why. If I have x1 of t plus, if I input this, a times x of t, I get out e to the a x of t, and that is clearly not equal to a times e to the x of t. So it's not linear. And let's consider time invariance. Well, let x of t be correlated to y of t. If I time delay x of t, then what I obtain is e to the x of t minus t naught, but then we realize that this is precisely just y of t minus t naught. So that's nice. Question. Wouldn't the eigenfunction property say that it's to be multiplied by negative 4n? Uh, well, it said yes, it's by 4n, but then we say of magnitude of y1, and so we choose y n equals 1. But yeah, I mean technically you're right, yeah, but I just chose to simplify it earlier. Anywho, so for time invariance, we have time invariance, check. For causality, just think about it. the output the value at any point t only value, like how do I put this? Um, let's say, okay, let's say y of t is my output, right? Then consider like um what does the value y of t depend on? Oh, well, of course, with respect to x of t, right? And we realize that, or maybe even like choose a particular t, maybe like y of 0. Then we realize that y of 0 evaluated is dependent on the value of x evaluated at 0. You see? You see that? And so because value of y of, maybe I'll just say t prime, depends on value of x of t prime, precisely, not anything, not any x of t where t is greater than t prime. Essentially, I'm not peeking into the future. The expression of the output explicitly tells you that I am not peeking into the future. I'm only depending on the value now. And so with this kind of like ideology, you could conclude that it actually is causal, because that's what causality is. Causality basically says I am not peeking into the future. I'm only depending on past values in order to deduce my current output. And lastly, do we have Bibo? And I will say that if x, absolute value of x is less than m, so like for all values of t, if this function is bounded, then I claim to you that the value of this is also bounded. Um, this implies that Bibo check. Does that confuse anyone? I'd be happy to clarify, but I feel like this comes very like this comes pretty intuitively in the fact that like if I'm evaluating my exponential at only like a bunch of finite numbers, then my result will always be more finite. For causal, it only depends on past and present values of t. Correct. Yes, that is the best way to think about it. So essentially, we get time invariant, causal, Bibo, and not linear, and so we get this fall. Okay. What is Bibo? Bibo is bounded in, bounded out. Essentially, that's saying if I have a bounded input, as in my signal, if I draw out my signal, oh no, I could bound my signal between two different lines, negative m and m. Then, like this is a bounded input. If I give you this any bounded input, then my output will also fit between two nice lines. Essentially, it will like the energy will not never go to infinity. Well, never go to infinity, yeah. Well, I mean, it can, but essentially the value can't go to infinity if I give you a finite number. Suppose rect of omega minus 1/2 is the Fourier transform of the input signal to an LTI system, whose frequency response is h of omega. The real and imaginary parts of h of omega are plotted below. If y of omega is a Fourier transform of the output signal, then what is the value of that? Okay, so it's important to see that let's say this is x of omega. X of omega is equal to 1 from omega being 0 to 1/2, 0 to 1, and 0 else. And so if I ask you what y of omega is, this is, wouldn't, would you be convinced when I say that, okay, well, maybe I'll just draw it out. write it all out. This is um, omega plus 1 plus omega j times my little function over here. Then what can't you say that the product of these two is just precisely omega plus 1 plus omega j from 0 to this and 0 else. So I basically obtained my y of omega that is like algebraically. I just recovered y of omega algebraically. And all I need to do is integrate over this or integrate over the magnitudes. So let's consider the magnitude. This is equal to the magnitude of omega plus 1 plus omega j for these numbers, 0 else. And then let me just find the magnitude now. It is square root of omega squared 1 plus that, so it's 2 omega squared plus 2 omega plus 1. From 0 equal to that and 0 else. And now all I want to do is integrate over that from 0 to 2, or integrate that squared, thank goodness. So integrate from that 0 squared is equal to the integral of 0 to 2. Oh, but then you realize that the magnitude of y of omega is just 0 for everywhere outside of these boundaries. And so we could kill this integral's bounds from 0 to 1 only. And then we take 2 omega squared plus 2 omega plus 1. And now we just integrate this, which is actually very nice because we have a 0 bound at the bottom. It is 2/3 omega cubed plus omega squared plus omega root 1. And thus this is 2 plus 2/3, which is 8/3. Voila. Okay. Let me just zoom out so that everyone can see what I did there. But otherwise, I'll keep going. All right, next question. Circuit question. Perfect. In the circuit below, the three resistors have resistance 2/3 ohms. The voltage. Oh, this is a very nice question. Yes. What is the current IT? Oh, okay. So we know that current, the current phasor is equal to the voltage phasor divided by the resistor phasor. And in fact, I'll say RAQ because we could convert this into a model such that it is a voltage source, Thevenin equivalent, and a current. And so now it suffices to find RAQ. Well, RAQ is equal to, that's all, so it's just, no, R plus R parallel R is equal to 2/3. R parallel R, this would be 4/9. I'm going to skip some math here, put over 4/3, which is equal to 2/3 divided plus 1/3, which is, oh, that is very, very convenient. That is crazy. That is crazy. Okay, sure. And so what I see here is that my input is actually two different phasors. And so you can interpret this as an LTA system, and you could decompose my input phasor into two input phasors. And in fact, I will actually convert them into phasor form. 3e to the. And I will actually input them individually into my system. And what do I get out? This is just, this is I equal to V over REQ, which is actually just exactly itself. And similarly, v2 is equal to v2 over r dq, which equals just v2. And so the summation of these should yield us just the summation of itself. And so now all we need to do is convert what we have here into a phasor form. Well, V1 as a phasor or as an actual like sinusoid is cosine. What is equal to 2/3. And remember, omega equals 2. So this is converted into 2 times cosine of 2t plus pi over 2. And then V2 will yield a input signal as follows. And so all we need to do is sum both of these and then obtain our final answer, which is y of t, which is like, we take the sum of these and we get a desired answer. So that's just a pretty standard question. It's pretty cool that it just ends up being one and saves you a lot of work. But in reality, you don't need to remember, you don't need to write out any of this. You just say, oh wait, if I realize that my input-output relationship is basically just equal to like itself, like it's an identity. It's the identity relationship. And so all you need to do is directly convert your input into the signal form, in time domain form, and then you'll be done. So it's just convenient. Anyways, 32. We have 5 more questions. 32, 33, 34, 35, 36, yeah. Suppose x of t is an even function, and we have that for all t greater than 0. If x of omega is the Fourier transform of x of t, what is the value of that? So 2 things. First of all, we realize that x of t is an even function, and we're given this. So for all t greater than 0, we're given this, which means that it's kind of going to look like this. And it's even. Because x is even, we know that x of t will look something like this when t is less than 0. So this is from x of t is even. And now, now that we know the full equation, we know what x of t looks on the entire line, we could use Plancherel's or Parseval's or Fourier transform Parseval's, whatever. It's been stated multiple times. We have the following. And then this means that our desired integral is equal to 2 pi times the integral of the magnitude squared of our function. And we realize that this is actually just the integral of this is just 2 squares. 1 square, 2 square. And so we just get 2 pi times 2, which is 4 pi. Voila. Anyways, next question. 33. Oh, I will hover over this just for like a second or two. People could see. Okay. All right. 33. F of omega is a Fourier transform of a signal that looks like that, and it should ring bells that this is a periodic function, and this is in the form Fn times e to the jn omega naught, where omega naught is equal to 2. What is this? So remember that any function that has a Fourier series, you could you could obtain the Fourier transform using this. Remember that given a Fourier series, you have that the Fourier transform of that function is 2 pi times Fn delta of omega minus n omega naught. And this is now equal to, well, we could just directly find it. 1 over 1 plus absolute value of n, delta of omega 2n. And now let's try graphing this out. Equal to f of omega. We realize that the delta functions are spaced out by 2. And what are we integrating over? Well, our region of integration is from -3 to 3. And where is that? That's from -3 to 3. How many delta functions fall into that region? Well, we only have, in particular, 3. And this is the n equals 1, n equals 0, and n equals -1 cases. And so each of these will be 1 over 2 delta of omega minus 2, sorry, omega plus 2. This is 1, this is just delta omega delta of omega. This is 1/2 delta omega minus 2. And so if I take the integral of this over this region, then what this would be is this would be just the integral over, I'll write it out this time. Maybe I'll carry this down. I'll write out this time. This is the integral over all these delta functions. And remember, if you're asking where all the other delta functions went, they're all gone because they're outside the region of integration, so they're kind of irrelevant. You're not integrating over them anyway. It's like saying, oh, I have a unit step function that I'm integrating over from this point to this point, right? Then if I'm integrating from some like 3 to 6 of the unit step function from here, I might as well just integrate over to function 1 because in this interval, my function is just 1. So essentially, I'm just simplifying my integrand and my bounds by using the fact that some things behave differently and more simply in the integrating bounds rather than when they're on the outside. And so what is this? Well, this is just directly from what we know. This is just 2. And we saw up here that, hold on. I think I missed out on this 2 pi over here. This should be 2 pi. There we go. Sorry about that. So this is now 2 pi over that, 2 pi over that, 2 pi over that, and thus this is 2 pi times all that, so it's just 4 pi. There you go, voila. Not too shabby. Yeah, I forgot to factor in this little constant, and hence it was off by a factor. But the ideas remain the same. We're almost done. We have 3 more questions. Yeah, and let's try to get this done before 12 so that people can go sleep. If the impulse response of the linear time invariant system is sum of deltas, what is the output of the system when the input is that? How convenient. This is just a convolution question between delta functions. We have a delta located at 1 plus a delta located at -1 convolved with delta located at 2 plus delta located at -2. And remember, every single time I say this, but you could just treat this like polynomials, multiplying polynomials. And so I will obtain delta located at 3 plus delta located at 1 plus delta located at -1 plus delta located at -3. So this is equal to delta t minus 3 plus delta t minus 1 plus delta t plus 1 plus delta t plus 3. And so I get this answer. Nice. Perfect. Let me actually draw the lines for this. It's actually very helpful if I do that. It should be just a quick few lines. Oh, hold on. That's not the right line. Let me do cold colors for this. Oh, shoot. That's foil, and then this last one. There you go. All right, I just want to make that elaborate. Anyways, last two questions. What is the inverse bilateral Laplace transform of that if the bilateral Laplace transform exists at that particular number? And that is actually a purely complex number. And so first, let's actually try to identify the poles for this. Clearly the poles for this, or maybe we could do partial fractions first. We set this equal to a over s minus 1 plus b over s plus 1. And we realize that a s plus 2 plus b s minus 1 must be equal to 1. This tells us that as plus bs is equal to 0, and 2a plus minus b is equal to 1. Well, this tells us that a is equal to negative b, and thus, wait, no, hold on. Actually, I think I'm right. Huh, that is rather weird. S minus 1, S minus 1. Yeah, I guess I'm fine so far. And I get that a, this is equal to 3a is equal to 1, implies that a is equal to 1/3, and thus b is equal to negative 1/3. That does not feel right. But I will hold on. Let me think about this. Think about this for a second. Yeah, that's fine. Never mind. That's right. Yeah. Okay. And so we realize that 1 plus using partial fraction for decomposition, I decomposed. Yeah, that's true. Yeah, okay. Sorry. I just have like gut intuition instincts that sometimes go off sometimes. So I get 1/3, 1 plus s, the s plus 1, plus or minus 1/3 s plus 2. That's a minus. And so we realize that our poles are located at 1 and negative 2. Those are my poles. And we now need to consider where is the region of convergence. But we know that it converges for this number. So converges at e to the power of j3 pi over 2, which is just equal to negative j. So it converges here. What should that tell you? This tells me that the one with the pole at negative 2 must be causal, and the one with the pole at 1 is anti-causal. So this is anti-causal, and thus my inverse Laplace transform should be e to the t u negative t 1/3. We're using my Fourier in Laplace transform pairs, and 1/3 this is causal, and so this should give me 1/3 e to the negative 2t e to ut. Voila. And thus we get the final answer, which is negative 1/3 e to the negative t e to t u negative t minus negative 1/3 e to the negative 2t u of t. That looks right. And so obviously we could factor out our 1/3 to get a nicer answer. And we are done. Questions, comments, concerns? All right, last question. I'll do this last question, and then you're free for all to answer questions or shoot questions at me. What is the convolution of cosine 220t and no? Huh. What an interesting question. Hmm. Huh. Okay. Well, if I convolve these two, let's consider the Fourier transform of that. Then this is equal to the Fourier transform of this multiplied by the Fourier transform of this. Yes. And then what we see is that this is delta functions, well, pi times delta functions placed at negative 20 and 20. And we're multiplying this with another delta function 30, delta function at negative 30. And so let's actually just think about this. If the delta function here lives consider taking the product of these two functions. In fact, I'll actually change the color for these two. Because this is the product of these two functions. Observe that this product is just 0. And why is that? Well, you can think of it in multiple ways. But the best way to think about it is if you take this product, you're going to get like something like this, or some terms that look like this. Example, let me just take an example. Consider this function. What we observe here is that, well, what do we learn about delta functions and multiplying with other functions? This takes just the value at omega equals 20. So it's 20 minus 30 times omega minus 20. This is delta function, the value at negative 10. And this is 0. So what you essentially see is that whenever you're multiplying delta functions together that do not overlap, you just get 0. And so this big little expression here, you don't even need to evaluate it. You'll think about like, wait a minute, there's a product of a bunch of delta functions that don't overlap at all. Then every single delta function will die out because as it takes the value of the other function, it'll just evaluate to 0. And thus, we get that this entire expression is just 0, and thus your answer is 0. All right, we're not done. But again, I'd be happy to go back to any question, but otherwise you're free to, you were always free to exit, but I'd be happy to go back to any question to re-elaborate because I did kind of rush the end because I didn't have time or we're running out of time, but I don't want everyone to stick around for too long. So if you have questions, please tell me. I think I have volume, so I'd be able to listen.
For question 21,
Yes.
the one where you switch the order of the impulse responses,
Oh, yes,
I
that one.
understand how it was done, but I guess like I wasn't so sure how to recognize that and see that pattern that you can use the commutative property in that way. Like I guess what would be like a good instinct to kind of develop with that?
Oh, so you're asking me when should you feel incentivized to switch the two? Is that
Yeah, and then like I guess in this special case, since the system two is taking the derivative, then it could be a
Mhm.
lot simpler. But then like I didn't really easily see that connection that I could switch H1 and H2, and then all I'd be doing is just taking the derivative. So I ended up using negative rect t, which was more work and a lot slower.
okay? So a lot of like a large portion of these kind of like planning skills come from either exposure or we're like so the exposure thing is just like whatever. But in this particular question, it's like you have to have some foresight of what you might need to do. So when I first saw this question, I had two routes. Either I just go the normal way or I switch to two. If I do go the normal way, um, no, I'm not evaluating anything. I have to, just in my head, I'm thinking about, okay, I have to do this particular task, right? And doing this particular task, obviously doing this in time is not going to be very fun.
Mm.
If I take the Fourier transform of this, it's going to be a rect function times a delta function.
Mm.
And so, that actually seems like it'll be all right. So maybe going in that direction will actually not be as bad. I'll be completely honest. But how do I put it? And then I'll have to take the Fourier transform of that, which will be like, okay, So
Yeah, yeah,
I'll mentally plan out in my head. I will take the Fourier transform. So step one, I'll take the Fourier transform of two things, and then I will bring it back into the time domain, and then I'll take the derivative.
Mm.
That's what I would do. Like that is the sequence of actions that I would think about doing when uh I'm
yeah,
doing the normal way. But if I take the derivative first, then I immediately see, okay, if I take the derivative first, I just have delta functions. And if I now I just need to do a convolution of deltas and some random function. And I'm done. It's just two-step process. So
yeah,
I made this mental map of the steps, and I was like, oh, I'm lazy. I only want to do two steps. And so which is why I took it this way. But I'll be
yeah,
completely honest, doing this way, it's not that bad either. Like, because
yeah, yeah. I
it
think
wouldn't be too
it's
long.
I think maybe the issue is like I guess I saw that the first way was possible and that
Mhm.
like it seemed solvable and then I just jumped straight into it instead of like stopping and seeing, okay, maybe I can actually switch the order and then it's a
Mhm.
more efficient solution.
Well, I feel like if you truly write it all out, it'll be around the same. The truly the ones where like you need the gut reaction or like the ones where we saw upwards, and those would truly like genuinely require
Oh,
the mental map kind of thing.
with the like delta functions and the
Where is it? Like something like this. Something like
yeah,
this
yeah.
would be like you are okay, well, this one is very obvious that you will not evaluate the Fourier transform of every single one, but it requires for you to like think about, okay, um, you kind of at some point you have to think about like not put away all the constants away and just think about the shapes.
Yeah, yeah.
And believe it or not, a lot of DSP and even grad DSP kind of ignores the numbers and you just think about where you're placing these spectrums.
Hmm,
So
hmm.
having these kind of intuition built will be very helpful in the long run. But essentially what I'm saying is, um, what was I about to say? Uh, you need to have a mental map of, or it's good to make a mental map of your work before you do your work. And
Yeah,
then
makes
it'll
sense.
be nice to like kind of check or maybe see, wait a minute, there's an inconsistency here. Maybe you could check on that. And then that's how you can easily debug your work along the way as well. That's just
Okay.
nice.
Thank you.
Yeah, of course. The number 29, uh, over this one, yeah. Give an example of a non-Beebo stable system. Oh, okay, I'd be happy to. So, example of non-Beebo. X of t, I put into system, and I give you x of 1 over t, or x of t over t. Then, if I say x of t equals 1, then my output would be 1 over t. And so I gave you a bounded signal. This is obviously bounded because it's just like, it's just this. And clearly I could sandwich it between a maximum and a minimum. But my output is something that's not so nice. It's something that goes to infinity. That's an example. Of course, this is a very simple example, and some things that we give you may not be as easy to analyze. Yeah. Anyways, I'm gonna be around here until like everyone gets their questions out. So Please feel free to shoot them. Okay. All right. Well, thank you for coming. Again, I'm still gonna stick around until everyone leaves. Just let me know if you have any questions. Of course. I think this is a long time, but cosine AT BT is always convolve unless A equals B. Yes. Yeah, this is true. You should ask Corey, you should ask your questions in the public chat instead of gatekeeping the knowledge. But basically, Corey asked, cosine of AT convolved with B cosine of BT is equal to 0 for any AB unless A is equal to B. And that is true, just because of the Fourier transform thing. Okay. I do not know if Calkin has office hours on Monday. I'm going to stop the recording now.